All right. Hello, everyone, and thank you for joining me for a very special episode of Handmade Hero. As you know, one of the things that we have put off for a very long time in Handmade Hero, and that I intimated recently that we would probably not want to put off much longer, is getting rid of the few, I think there's only three functions that we still call from the C standard library. Because right now, Handmade Hero pretty much doesn't use any external code at all, but it does still link with the C runtime library. And the only reason we're doing that right now is because of cosine, sine, and atan2 are the only things that we actually call. And so at some point, we really wanted to get rid of those for a whole number of reasons, some of which we'll actually be going into in a moment, I think, as well. But one of the big problems with replacing those is I am not a numerical programming person. It's not something that I spend a lot of time doing. And so when I go to replace sine or cosine, typically what I do is I just look up somebody who's already figured out how to do a good replacement for sine or cosine and just do some version of that code. And that is not a very good explanation, and it's certainly not something that's going to help anyone watching the stream know about what goes into this sorts of replacement and this sort of mathematical coding. So I was kind of hoping that someone could give us a better explanation of that and kind of give us more of the details about how one goes about truly replacing sine or cosine or atan2. Atan2, my understanding, is significantly harder. And so thankfully,
Definitely.
as you know, way back in the early days of Handmade Hero, on the chat, pseudonym73, who you haven't seen much because unfortunately in the recent days the stream time has moved, was always kind of our guardian angel of math and would kind of jump in to help us anytime when I was like, and I think there's probably some math thing here, but I don't know what it is. So
Yes.
I knew that he was into this sort of programming and had a lot more experience than I did, so I asked him. His actual name is Andrew Bromage. I now know how to pronounce that correctly. And he
Very
lives
good.
in
And now
Australia.
all you do. Yeah.
There you go. And he lives in Australia, so we set up a stream time. We were trying to work out a stream where he'd come on and explain this to us. So I'm honored to have him on the stream. And although our connection's not great because we're going all the way from Australia to me to Twitch, which is probably not the best thing in the world, he's gonna try and walk us through this. First of all, what this kind of programming is all about, and how one goes about doing something like sine and cosine replacement. So with that introduction, Andrew, over to you.
Okay. So we'll try and do this I think we'll try and do it as a conversation. I've got a whole bunch of notes here which I will dump on the Handmade wiki at some point soon. It just needs a little bit of editing.
Awesome.
So right. So the basic idea is what you have to understand first is how numbers are represented by the computer, and floating point numbers in particular. So this is all covered in this wonderful document, which you probably can't get access to, which is the IEEE Standard for Floating Point Arithmetic 2008 edition. This is kind of expensive. I think it's like 50 euros or something ridiculous like that. But if you happen to have a institution that will pay for access for you, all the better, like me. The IEEE standard grew out of a bunch of incompatible computer arithmetic systems from the 70s and 80s. But thankfully for the PC industry, it was largely based around, they based this on Intel's standard. The basic, so, okay, let's step back for a minute and talk about how you would represent a number. By the way, I'm going to assume that everyone can kind of read binary and hexadecimal, because if you can't, you're going to get lost very quickly here, because we're going to go into actual binary representations.
And I will scold them thoroughly if they
The
don't
thing
know
I'm
how to
going
do
to
that
assume you
after
know.
this many episodes of
Yeah.
Handmade Hero.
Exactly. We will not assume octal.
Okay. Yes. Yes.
Because who uses octal, right? Okay. Need to know is some basic high school maths. And the first thing we're going to look at is scientific notation. Scientific notation is where you represent a number like, say, I don't know, 1024 is 1.024 times 10 to the 3, or as we say in C notation, 1.024 E3. If you understand what that means, the rest should be easy. Well, not easy, but straightforward anyway. So in scientific notation, what we do is we take a number and we represent it in two parts. One of them is a number between 1 and 10, including 9, not including 10, and then times 10 to the power of something. And that's what shifts this decimal point. You can shift this decimal point backwards and forwards by changing this number here. The terms for this is the mantissa. I'm going to spell it out for you because that's a technical term. And this number here, this 3, is called the exponent. Oops. And these are kind of the two important numbers in a floating point representation. The way that IEEE 754 represents numbers is exactly the same as this, except of course it's not in decimal, it's in binary. So if you have a number like 1.1110110, blah, 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 in binary, right? So this is a binary number. This is not a decimal point, this is a binary point. In scientific notation, it would be times 2 to the, right, maybe not 53, that's a big number, 6, there we go. And this is equivalent to the number, whoops, by the way, this is a MacBook Pro. Anyone who has a modern MacBook Pro knows what I mean about the keyboard on this. It's absolutely terrible. Everyone complains about it. The lack of an escape key is the least of your problems, although it is a big problem if you're a VI user like myself.
There's
anyway,
no escape key?
No.
Oh my.
There's a touch bar.
Oh like my goodness. Okay. Oh, we seem to have lost Andrew. Oh no. I wonder if the MacBook has decided to take revenge on us here. I shouldn't have said anything. Is it dead? Let me see here. Oh, there it goes. Well, that's a problem because we've only just begun our replacement for sine and cosine, so I'm not sure how to get it back. Okay, the link between here and Australia is not that bad, though. Google, come on. Surely it can't be this bad. Unless the MacBook really did. Well, we will wait for a second and see if we can get a get it back. In the meantime, I will take another bite of this. Oh. Oh. Is it coming back?
Hello, are we on now?
Yes. But only your voice.
Excellent.
Oh no.
Okay. Are we on now?
Just your voice, not your screen.
No, okay. All right. Ladies and gentlemen of the audience, you have to understand a little thing called Australian Home Internet. we don't, I don't have NBN yet. Not in this era. Is the screen back now?
Yes, it is.
Excellent. This will probably happen again
Okay.
over the course of this show.
We will struggle through it. We'll figure out a way.
We will figure out a way. All right. So I got rid of the video of me down the bottom left because I think that's probably just increasing the bandwidth unnecessary just to see my face. You probably don't need to see my face. We might bring it back up again for the Q&A.
Sounds good.
Okay, good. So what I was saying is that this number is kind of equivalent to this number. 2 to the 0 is, of course, 1. And this is the idea of the name floating point, is that this binary point can float around by altering the exponent. What's important for us, though, is this number, this representation. Most numbers can be represented. Let's make this a negative number, just to make this absolutely clear. Most floating point numbers can be, or most numbers that we want to deal with can be represented in 3 parts. One of them is this, which is the sign, whether it's positive or negative. The second part is the mantissa, which is this part, which is a number between 1 and 2, including 1, not including 2. And this number, which is the number that you raise 2 to the power of. And that part is called the exponent. And the obvious number that you may think can't be represented in this way, and you'd be right, is 0, and that's a very important number, and we'll deal with that in a minute. But most numbers can be represented this way. And the way we do it in IEEE floating point is we pack these into bits in the following way. I've actually got the standard here, so I can show you. Somewhere here. That's decimal. We don't care about decimal. The IEEE standard covers a lot of ground, and I'm going to introduce you to some of the really weird parts later, not in detail because you really don't want to know. But no, you really don't. But I have an example. Here we go. This is what I'm looking for right here. So this is the format. We have 1 bit which represents sign. It's 0 if the number is positive and 1 if the number is negative. This is the exponent field. And the way we represent that is we represent this in a field that's W bits in size. Now, in the case of binary 32, which is what Handmade Hero calls real 32. And by the way, this is a finite set of numbers. There are 2 to the 32 possible binary 32s. They are not real numbers. It's finite. Anyway, that's neither here nor there. That's an argument for another time. The way we represent this is we take this number 6, and then we add to it 127, which is 2 to the okay. So this field in binary 32 is 8 bits in size. 127 is hang on, is 100 to the 127? Let me just check that because I have it here. Yes, bias 7F. Yes, that's 127. So we add 127, and then we store that number in the field. That's what 133. Now, for those of you who, of course, know about binary representation, may wonder why we don't just use the 2's complement here. There is a good reason for this, and we'll get to that in a minute. But anyway, that's the number we store, 133, which is the exponent plus this number, which is called the bias, and we'll go through all of this in a minute. So that's how so we have 1 bit, which is the sign bit, and 8 bits, which is the biased exponent, the exponent plus a bias. The final thing is how we represent the mantissa. In this case, this is the mantissa. One of the interesting things about scientific notation is, for any number other than 0, this leftmost digit is always a 1. it's never a zero, because that's what we mean by this kind of normalized scientific notation. So we don't actually need to store that. So we strip that off and we store that bit pattern. And that is called the significand, the trailing significand field, as it's called in the standard. And with that, you can store any what we call normal number. Now, there is a useful little tool here. Float, it's called, let me search for float toy. There we go, float toy. Oh, hey, float toys. Wonderful little thing that someone has stuck on GitHub, which lets you actually play with this. So you can flip the sign bit and it'll make it a negative number. You can play with the exponent. You can play with this and have a lot of fun with this, with various bit patterns, and see what floating point number it corresponds to. It has 32-bit and 64-bit. So if you want to work with this in a little more detail and get a bit familiar with this, I use this a lot writing the notes. It's a very useful little thing to know about. And it's got links to the Wikipedia pages on single precision, double precision, if you want it explained better than I can. All right, so that's how what we call normal numbers are represented. By my use of the word normal number, it suggests there's some other kind of number that's not normal. And the main other kind you need to know is what's called subnormal numbers. Now, this is this word was introduced in the 2008 standard. Before that, people called them denormal numbers or denormalized numbers. But I'm going to use the new note, the current terminology, even though subnormal sounds, I think, quite totalitarian. Nonetheless. So the idea is that for the exponent field, we reserve 2-bit patterns. In this case, there are 8 bits. We reserve that one, which is all zeros, and this one, which is all ones. So these do not represent the normal exponents. You don't subtract 127, and that's what it is. 0 is the interesting one from our point of view, because what 0 means is that this is a subnormal number. And what that means to the floating point implementation is it means that the exponent is set to minus 126. And the mantissa, the significand field, is interpreted as a mantissa without a leading 1. So it's with a leading 0. So if you were to see, for example, this pattern, whoops, oh, I hate this keyboard, right? What that means is this means that number times 2 to the power of minus 126. And what this does is this gives us a representation for very small numbers. Very small numbers are sometimes important in floating point, but more importantly, it gives us a representation for 0 by simply making it all zeros. It's I think there are 23 of them, so it's that. And there's the sign bit at the front. So that is the representation for 0. And the reason for that is that we use the reason why we use the all zeros in the exponent field for this is because programmers really, really like it if when you have a block of memory and you fill it with 0 bytes, that means the number 0. It means when it's an integer, and it means that when it's a floating point value as well. And this is a very highly desirable feature of the number system. Okay, so those are really all of the finite numbers that we have to worry about. This bit pattern 1 is reserved for 2 other things. They're infinity and a special value called not a number. You will see these. If you've ever worked with floating point, you will be well familiar with not a number and infinity, not a number more so. these are there to make the system algebraically closed. Now, what that means is that any operation gives you a meaningful answer. So, for example, if you divide 1 by 0, what you get is infinity. That's not a finite number. And in fact, you can usually set, in fact, no, you can set your floating point unit to give you an exception if that ever happens. We really don't want that in a program like Handmade Hero. But it at least gives a meaningful answer for that. And if you divide, you get negative infinity. Not a number is for situations where the answer really isn't a real number, like the square root of -1 or 0 divided by 0. Oh, one thing I didn't mention, by the way, is that is also a possibility. And what that means is negative. Now, you may wonder, what's -0? Why would you need it? And you're right. That doesn't make any mathematical sense. But it does, there are some uses for it. Because often what will happen is you do some calculations, and the number just gets too small to represent. And by making this a -0 is at least it tells you which way, that's called an underflow, by the way. And what that does is at least tells you which direction it underflowed from. And so that's a sometimes useful feature of the system. Again, it's there mostly for algebraic closure reasons, not because it necessarily makes any mathematical sense to have a -0. But it's useful in practice. So that, in a nutshell, is IEEE floating point. Oh, just so we're absolutely certain what we know this. So there's a sine bit, all ones. Infinity is if this field is all zeros. That's a representation for infinity, the sine bit, whether it's positive or negative infinity. This, the sine field, is currently ignored at the moment. 122. Sorry. Whoops. So if you have that, that's where non-zero pattern, that is the representation for not a number. And by the way, there are two kinds of not a number. One is if there's a 1 bit here, and one is there's a 0 bit here. But clearly, this part here has to be non-zero if that's 0. This is called a quiet. This is called a quiet nan, quiet not a number, and this is called a signaling nan, signaling not a number. And the difference is that quiet is just propagated through your calculators. If it was basically, if you try and do anything with get not a number as an answer, and a signaling not a number is one that always raises an exception no matter what. So that's something that you may have to know, but that's basically all of the tricky cases. So you've got normal numbers, subnormal numbers, and then these special cases: infinity, quiet nan, signaling nan, and that's everything. Once again, this sine bit here is currently not interpreted by the standard. I'm sure that some future standard will take a liking to that and use it for some reason. All right, so that's the basic idea of how floating point numbers are represented. So what we have 1 bit here, 8 bits here, and 23 bits here, and that should add up to 32. So that's the binary 30 representation. Binary 64. The sine bit's the same size. This is a bit wider. This is a bit wider. But otherwise, it's the same idea. Any questions about any of that, or is that?
So I don't think I had any. I'll look briefly at the chat to see if there are any questions about that are coming through. If anyone wants to put a Q colon, I will double check it. But that was pretty clear. I had one question while I'm waiting to see if anyone anyone had something they didn't understand. I did have one question, which was, so with the let me look back over here. I should have written it down at the time, but I thought I had to. Oh yes, so it's just a peculiarity of binary as a number system that you can skip encoding the leading digit, because any other number scheme, it's always just the base of the number minus 1 that you would have to encode there probably, and just since 2 minus 1 happens to be just 1, you can skip the encoding. But it seems like that's just like we got lucky with binary in a sense. Is that
well, yes, you're kind of right. On the other hand, it's one of the reasons why we use binary.
Yes,
to do
yes,
this, right? Yeah. But yes, if you are encoding decimal, and the standard has a way to encode decimal in here, you have to store a number between 1 and 9.
Yep. Okay.
Yes, this is why these formats are called binary 32 and binary 64. Once again, this is new language in 2008.
Interesting.
New in 2008, I know. Yeah. Before that, they were called single precision and double precision.
Got it.
We still mostly use those terms, but it's binary as opposed to decimal.
Okay, so we had one question from the stream on that. So very good explanation, by the way, because I think everyone got it, including me.
Oh, thank you.
Is there a representation for underflowing numbers? I think that was just a question regarding so when you do have an underflow there, you lose all information but the sign bit. Was I correct in understanding you there? So when there's an underflow, it'll go all the way down to subnormal, and then it'll just be left with just the sign bit and zeros eventually.
That is correct.
Okay.
Of course, there are the standard and your floating point unit as well has a way to turn an underflow condition into an exception.
Okay.
If that's what you really want. Sometimes that is what you want. It's called what's it called? Loss of significance, I think.
Okay. Sounds existential.
Yeah. Yes. Exactly. It is very, very, very existential. Yes. Or loss of precision or something like that. Anytime you go from normal to subnormal of your significand, you don't have as many bits available to represent your mantissa as you might want.
Yes.
Hey, here they are: binary 16, binary 32, binary 64, binary. So we've got half precision as well.
Interesting.
Decimal 32, decimal 64, and decimal 128. Those are the main versions that are in the standard.
Interesting.
So there you go. I accidentally landed on that page.
Okay, so yeah, I don't think there were any real questions then, other than that one. So you take it away.
All right, now we will go on. So let's have a look at the little header file I wrote you, which is it's Handmade numerics. So I've put it under an MIT license, so anyone can have a copy of this. And this defines a lot of the constants that we need floating point numbers at the bit level. Are those colors all right, by the way?
Yeah, look fine to me.
Yeah. Okay. Cool. Good. I haven't had full coder bug yet. Well, mind you, it's not available for the Mac anyway. So
it isn't. I think it is.
That wasn't. Isn't it?
Yeah, I think it is now.
All right.
Big news.
Okay. I didn't mean that as a hint.
Okay.
Yeah. Okay. So the main things here are the number of bits in the exponent, the bias for the exponent, which by the way is always 2 to the number of exponent bits minus 1 for any floating point format. That's what it is. The significand bits, it's not the mantissa, it's the significand. And the mantissa is the number of bits in this plus 1.
Yes.
Is 1 point something. The significand is but you knew that. All right. The minimum and maximum exponents, these of course are not symmetric around 0, and the reason is because we reserve 2 values, one for subnormal and one for all of the other special cases, for things that aren't finite numbers. Then we've got a bunch of constants here. Now, these, by the way, the C standard library does define something very like these. And let me just show you what they are. They're defined in float.h. Whoops. No, I don't want to enable Siri, you fool. C float.h. That's unfortunately right next to the delete key, and it's on the touch bar on this
That's
Mac.
amazing.
So I keep. I know. Oh, it's crazy, absolutely crazy. All right. So is this a good? No, that's got lots of advertisements. We don't want to do that. Here we go. Wiki. That's probably good enough. You see how long this is taking, by the way, while I'm
Yeah.
screen sharing. Okay. Yeah. Yeah. Home internet. I'm telling you. All right. So this defines a bunch of constants that are very similar to the ones that I've defined here, but they differ in one slightly subtle way. So we've got minimum exponent, maximum exponent. This is for float. The maximum value. The minimum value, which, by the way, is not actually the minimum value for a float. It is the minimum positive normal number for a float. A lot of people hate this. That if float max is the largest float, float min should be the smallest float. Well, but it isn't. That's why I've actually called it max normal, and min subnormal in this. I think that's probably less confusing, that notation. This is just the sine mask, the exponent mask, the amount by which you shift the exponent to the right, the significand mask, and finally this number epsilon. And this is probably the most useful number of them all, unless you're actually packing and unpacking floats. If all you're doing is working with floats using the values, that you're the minus whatever. The machine epsilon is probably the most useful number that you'll see, and you'll find we use this in a few places in the code. Epsilon is not equal to 1.
Could you go back about 15 seconds? We
So
lost you for
for
a split second there.
Okay, and it was the most important thing.
Yeah,
it did.
It picked the worst time.
Okay, all right. Epsilon is the smallest number such that 1 plus epsilon is not equal to 1. So what this value does, this is actually 2 to the minus 23. If you work it out, that's 2 to the minus 23. So, because that's the number of bits in the significand. What this does is this gives you a measure of how granular the number system is. It's the smallest relative difference between two adjacent numbers. And so this is actually a really important number, because this is how you kind of this number, if you like, is the difference between a real number and a floating point number in some sense. And this number will turn up a lot of the time in what we're doing. So remember this number epsilon. I will explain it again when we see it in the future. But of all of these constants here, these are important for unpacking and unpacking floats at the bit level. But this is the number that you need the most for actually working with them. All right, what I finally got here is a union of a real 32 and a uint 32, and that's back. Could do it with a union, could do it with pointer hackery in C. Either way, I checked with a couple of compilers, and it does seem to compile this union away, which is what you want, because in modern Intel FPUs, in SSE, SSE2, it's what you have is a 128-bit register that you can fit 4 binary 32s in, 4 single precision floats, or 4 uint 32s. And all you have to do is decide that value is something different. You don't actually need to convert from one to the other to do bit hackery on it. And you want a representation where that is compiled away by the compiler. And I think most compilers are pretty good about this, because people who are doing low-level hacking with floating point numbers, they need a consistent way to just have some somewhere interpreted as a float, and now I want to interpret it as U32 so I can extract some bits from it. And so the union way seems to work on everything I've tried. I have not tried Visual Studio, so I might have to do some disassembly later just to see how that's happening. All right, so I've got a little enum here because this is useful for some of the basic operations to work out the numbers 0, normal, subnormal, infinity, or nan. We'll see an example of that in a minute. Just to be clear, what I'm heading towards, I've got a real worked example here of floating point division in all of its glory. You'll see what I mean by that in a minute. But anyway, so this is to test if it's positive infinity, negative infinity. This is sorry, no, these are values. This returns positive infinity. This returns negative infinity. This returns a quiet nan, which is I just set the significand to all ones. It has to be at least the first bit has the most significant bit has to be 1. I just set them to all ones. That's a fairly standard way of doing it. And now finally some queries. This is the first one: is a number a finite number? That means it's anything other than infinity or not a number, normal or subnormal. This is true if it's an infinity. This is all fairly straightforward, but you take the number x, you store it in this union as a float, you read it out as an integer, and then do whatever bit masking and mucking around you want to do. Again, this is for infinity. It's infinity if the exponent field is the special all ones pattern and the significand field is 0. This is true if the number is positive according to its sign bit. Of course, if it's not a number, then the sign bit doesn't mean anything, but that's all right. So here's the first useful operation, if you like. It's take the absolute value of a number. And all we do for that is we take this union, we store x in it, we mask off the sign bit, so we force the sign bit to be 0, and then just read the value as a floating point number again. And that gives us the absolute value of a number. Of course, there are functions to do this in the C standard library, but this is, and also you can use comparison and negative and so forth. But this should compile down to like 1 instruction, I think. Maybe a load of this sign mask, so maybe 2 instructions. But it's a lot of code to get 2 instructions, right? This is a function which sets the sign bit. So you take a number, you mask off everything but sign bit, you then set it. Yeah, a few ways you can do that. But anyway, we either set the bit if we want it to be negative, or we clear the bit if we want it to be positive. All right, this is the function that takes this enum up here. It takes a number and categorizes it as to what kind it is. So we extract the exponent field, the significant field. If the exponent field is 0, then it's either 0 or subnormal. 0 is a special kind of subnormal, but the difference between that and between 0 and a subnormal number is that a subnormal number, in theory, could be normalized if we had enough exponent. And we'll see why we might want to do this in the future. It's so that we can deal with most normal and subnormal numbers in a uniform way. And that's sometimes a useful feature. Then we've got infinity and nan, and those cases don't apply. That's a normal number. I think this is fairly straightforward, because what this really does is this just implements the patterns that we looked at earlier. All right, now this is where it starts getting interesting. Extract exponent. Now again, there is a function in the C standard library that does this. It is called frexp. Here we go. It's C++. C library function. Let's just pick one. Here we go. Microsoft. Let's look at Microsoft, shall we? So, frexp takes there's a double version and a float version here. The float version takes a float, returns a float, and also takes a pointer to an integer into which the exponent is stored. So what this does is this separates a number into its mantissa and its exponent. This is one of the most useful operations for very low level. Is this page helpful? Yes, it is. Go away. No, I'm not giving you feedback on the sleep stand. All right. This is, and the reason why this is one of the most useful operations is that it helps you reduce the size of your problem down. Now, let me give you an example of that. Let's suppose you're implementing square root. Right? We want to implement square root. So we know the zero case, we know the negative case, the square root of negative number is not a number. Infinity and nan, we don't care about those for the moment. We'll just look at positive numbers, whether they're normal or subnormal. We know that a number is m times 2 to the e, right? Where m is a number between 1 and 2, and e is some integer. If the exponent is even, that is, if this is actually to the 2p, then the square root of that number is the square root of m times 2 to the p, because the square root of 2 to the 2p is p. If it's an odd number, 2p plus 1, then it's the square root of m times the square root of 2 times 2 to the p. In either way, we've reduced the problem of computing the square root of an arbitrary number, normal or subnormal, down to the problem of computing the square root of a number in the range between 1 and 2. Reduce the size of the problem down so far for just a little bit of bit hackery. And of course, this is what your FPU does, because the bits are just there. And so that reduces, as I said, reduces the size of the problem down. This is what a concept that we're going to come back to, which is range reduction. The range of values that you have to feed to this function can be reduced dramatically to numbers in a very small range. So that's the reason why this is a very useful operation to have around. And we'll have a look at it in a minute when we look at division, because this is one of the things that I've done with division. So let's actually look at the implementation of that. Extract exponent. So there's a lot of code here. Some of it's comments, of course. So in the case of 0, infinity, or nan, we just set the exponent to 0 and set the mantissa to that. So there's not a lot you can do in that case. I think this is what the C library does by convention. Anyway, for a normal number, all we do is we extract the exponent field. We extract the exponent field, grab the mask, shift it by the amount that it needs to be shifted to bring the least significant bit to the least significant bit of this uint32. We convert it to a signed integer and then subtract the bias, and that gives the exponent. To get the mantissa, all we have to do is set the exponent to 0, which means we really set it to the exponent bias, because to represent 2 to the power of 0, we add the exponent bias to that. And so all we need to do is just force that field as if it was 2 to the power of 0, and that is the representation of our mantissa. So does everyone kind of understand that?
It makes perfect sense to me. I'll kind of eye the chat to make sure if anyone is
So if you have this ES sine, this is the mix up. So what we do is we extract bias to find out what the exponent should be, and then to return the mantissa, all we do is we just set this to, what is it? It's 0. It's this bit pattern. We just force it to be that. I think it's that. That's right, isn't it? Yeah. we force it to be that, and then that gives us a number that is where the exponent has just been forced to be 0. Okay. For the subnormal case, this is a little tricky. Now, we could find the exponent by extracting the mantissa and using like bit scan reverse. People know what bit scan. Have you used bit scan reverse? I don't know.
Yeah, it might. Some people may have forgotten, but in the Handmade intrinsics, there is a bit scan. We used it actually for doing bitmap extraction because the way that they store the bitmap code in a Microsoft BMP format is to actually just put the mask in there. So to figure out what you have to shift to get like the red out or whatever, you have to do a bit scan.
Yeah. Okay. So what bit scan reverse would do is if in the subnormal case, what you want to know what the exponent should be. We're storing the exponent as an int 32, so we're not constrained by the size of the field. And you could do that by extracting the mantissa and using bit scan reverse to find the most significant 1 bit in the mantissa. But the way I'm actually doing it here is just by multiplying the number by 2 to the power of 25. And this is, you can believe me that number is 2 to the power of 25. Calculate it yourself if you want to. I've only memorized my powers of 2 up to about 17 or so. And of course I know 32 and I know. Anyway, most programmers have memorized their powers of 2 up to a fairly modest number around the 16 or 17 mark. Most of them have not memorized 2 to the 25, but that is 2 to the 25. Multiplying a number by 2 to the power of 25, if it is a subnormal number, is a lossless operation. And this is another theme that will come up as we go on with this, which is that some floating point operations are lossless, that they don't involve any rounding. The result is exact. And multiplying by 2 to the power of 25 is one of those operations because it's just manipulating the exponent. And the FPU doesn't optimize that case, but it knows, but if you multiply a mantissa by 1, you get the same mantissa back. It is in that sense, it's a lossless operation. So what we do here is we do pretty much exactly the same thing here, except we multiply it by 2 to the power of 25 first. And then when we extract the exponent field, we just subtract off the 25. And then we set the exponent of this scaled number to 0, and that's how we deal with subnormal numbers in this case. Does that make sense to everyone? Subnormal numbers
I have one question.
Tricky case. Yeah, sorry.
I have one question about that, actually.
Yes.
So, assuming that a number is subnormal, it means that its binary pattern in the mantissa is implicit 0, then the binary point, and then some number of zeros, and then the actual 1-0 pattern that we have for it, right? When you do...
Sorry, you cut out there for just a second.
Oh, sorry, yes. So... If you've got a subnormal number, you've got bits at the end, you got the low order bit set, some number of zeros at the top.
Yes.
When you multiply by a power of 2, does the floating point unit first shift those numbers up to actually move them into the normal range, then start incrementing the exponent, or what happens exactly?
Probably what is going on, and you'd have to look at the actual circuit to find out what's going on. It probably does something very similar to what we're saying here. It probably uses something like a bit scan reverse.
Okay.
Because it's a fairly small circuit. So it probably operation something like this. It basically turns a number into its normal form to do work on it.
Okay.
In fact, of course, for those of you who are old enough to remember x87.
Oh yes.
This is pretty much exactly what happens. x87, 80-bit floating point numbers, the Intel Extended Precision, as it's known now, doesn't have subnormal numbers. It doesn't have normal numbers either. The 1 is always explicit in the significand of an 80-bit float. As I recall, I think that is the case. Vague memory of that. And so probably in turn using some kind of extended precision like this to do all the intermediate calculations. So it probably is turning it into some kind of explicit representation without an implicit one.
I see. So perhaps one thing it might do is when a floating point number comes in, it will turn it back into a normal number right there. Then it will do the operation, turn it back into a subnormal number if it had to. If it doesn't have to because it got multiplied up, then it just stays normal. Something like this. Perhaps.
Exactly. Or another thing it could do, it could have an internal representation that just includes another bit in the exponent field.
Okay.
And that's in normal cases to normal numbers.
Got it. Okay, thank you. I didn't see any questions in the chat, by the way, so you are good to go.
Yeah, cool. So the converse of this operation is scale by exponent, which doesn't necessarily have to be a number between 1 and 2. We'll relax that, and an exponent, and then puts it back together. There are a few more cases you have to deal with here because we could cause an overflow or underflow. Overflow being we can represent, and underflow if it's smaller than the number we can represent. And I just picked a number 500, which is kind of roughly it. That if it's less than 0, then it's then we return a 0 with the same sign as x. That is, we preserve the sign bit. So this is flow correctly according to the standard. If you underflow a negative number, you get -0. Sorry, Handmade Hero users, you're going to get -0s if you try this, but don't. An underflow is probably a mistake anyway, unless you don't care that it's close enough to 0. And again, for an overflow, we return infinity. And then now this is all the code that does the rest of it, and this is a bit nasty here. So for nan or infinity, we just return x. That's fine. And to handle the normal and subnormal cases, basically what I did here was exactly the same as above. I used 2 to the power of 25. I've got 2 to the 25 and 2 to the minus 25. So if we're trying to scale a subnormal number, we turn it back into the normal range. This again turns it into a kind of a normal number. X field is what is X field? So we pretend that we've got more bits of precision. This is in 32. For the subnormal case, we do that and subtract off 25. So that's if we're scaling a subnormal number. But there's also the possibility that when we scale by the exponent, we get a subnormal number. And for that, what we do is we just basically check it against the max exponent and the min exponent. If it's greater than the max exponent, we return infinity. If it's less than the min exponent, then this is a subnormal or underflow case, in which case we manipulate this by 25. We do that. So this is definitely underflow here. We just return sine 0. Otherwise, we add 25 to the x field, pack that as a number, and then return that value times 2 to the minus 25. So it's a case of unpacking a subnormal number. Packing a subnormal number, we just manipulate the x field and then multiply the value by 2 to the minus 25. You put on this exam, but that's it's this just an illustration of the kind of go to deal with the case between normal and subnormal numbers. And for the normal case, it's fairly easy. You just add the x field, exponent bias, shift it, and pack it all back together. So we can just use this as a box now. Now, this is probably where I should talk about the difference between this and the C standard. Because if you have a look at the thing, at the definition of f of x here, it says it splits it into a Manchester exponent such the absolute value of m is greater than or equal to 0.5 and less than 1.0. So the C standard doesn't talk about floating point textbooks do. It talks about a number between 0.5. This I this, probably too much time actually, trying to decide whether I should follow the C, the C convention on this, or I should follow the more usual floating point thing on this, and I decided to follow the more usual floating point thing. As a result, the other thing that this affects is it affects min exponent and max exponent. If you have a look at the value of min exponent and max exponent according to your C standard library, these numbers are different by 1. I think it's minus 127 to 126 or something. So that's the, if you like, the flip side of using this convention. But I don't know, should I have used the C convention? Because most people will be using it.
I tend to not care at all what's in the C specification, and double that for the C++ specification, just because I find that a lot of times their decisions are usually motivated by things that, well, in the C++ case, they're just motivated by lunacy. But in the C case,
yes,
they probably had a reason for doing it, but that reason is probably not particularly applicable to game programming necessarily, and probably had more to do with some case in scientific computing that was legitimate, but is not really what you want in the case of performance-oriented code that typically, flush subnormal to 0 is a typical thing for a game to do. It's probably not a typical thing for a scientific computation to do, for example.
Exactly. And look, to be fair, right, this part of the C standard probably predates the IEEE 754 standard by 10 years.
Yes.
Yes. It's because the first version of the IEEE standard was 1985.
Yeah.
And this probably is 10 years before that.
Yes, you're probably
right,
yes.
So it dates from the days when all of the vendors had their own different floating point standards, and they're all mutually incompatible and quirky.
Yes.
And there's a little quote here that I'm actually going to put. It's Wilkinson, not Wilsonson. I think it was like a Turing Award speech or something. It was called like Confessions of a Numeric Analyst or something like this, where this is basically a rant about the state of computer arithmetic in 1971. That one of the main virtues of an electronic computer from the point of view of the numerical analyst is its ability to do arithmetic fast. Need the be so bad. So that's the state of computer arithmetic at the time that the C standard, that C was invented.
I like the fact that he was upset about it in 1971. If he had seen it today, if he could see it today, I think he would probably just die immediately of shock. But
at least we have a standard.
That's true.
The IEEE standard is at least predictable,
yes.
And there's something to be said for that. I mean, the C standard doesn't even depend on these being binary.
Right. Yes.
One of the things that you'll find in there is the float radix. And it can be different from a double radix, at least in theory. And that is, I mean, you can assume that it's 2 because it's a binary number on everything you care about. But even so, right?
Yes.
Yeah. Anyway. All right. Enough of that. Okay. So that's the if you like the basic float operations, or at least the ones I needed so far. I'm not. This is the right set of basic operations, but it's probably good enough for what we're doing here. So let me walk you through division. Is floating point division without using the slash operator that divides 2 numbers anywhere. And the reason why I wanted to show people this is because when you step inside, like in your debugger, you step inside your C standard library's implementation of sine or cosine or something, there's a lot of stuff in there, and it doesn't look like calculation, quite a lot of it. And so the reason why I wrote this out is to kind of show you what all that stuff is. Now, I'm not going to go through that stuff in detail, All I'm going to do is show you that it is there and how much of it there is. And then this will give you an idea of then you may want to use the standard library if you're not doing general purpose computing. For special purpose computing like Handmade Hero, where you can assume some things about the values that you're going to give to your functions, you can assume that it's sine. If you try and take this, if you try and take the sine of 10,000 radians, that's probably a bug in Handmade Hero.
Yes.
Whereas the C standard library has to return a correct answer in that case for some definition of correct. And so it's to deal with things like that and to deal with -0 correctly, which we don't necessarily care about. It's to deal with positive and negative infinity. It's to deal with not a number. If you've got a library function that computes e to the x, if you give that negative infinity, that actually returns a reasonable answer. It returns 0. E to the negative infinity is 0 because that's, if your number overflows in that direction, imagine that it's just a number that's less than the largest representable number in that direction. That's a sensible answer. So anyway, so let's look at division. So this, if you like, is the finite number is the case where x is a finite number and y is a finite number, which is really the case that we're interested in. So that's normal and subnormal, including 0. We do have to deal with division by 0. That's something we probably can't get away with. 0 divided by 0 is not a number. Anything else divided by 0 is infinity, and it is an infinity of the same sign as x. So if x is, no, it's the sine of x exclusive ored with the sine of y. So if we take -100 and divide it by -0, we get positive infinity. This is laid out in the spec. Let me show you. Let me see if I can find this here.
So the sign of the divide still proceeds as if it were just a regular number.
Yes, the specification
just the number part becomes infinity.
Yes. So there's that. Let's have a look here. Division by 0 shall be an infinity correctly signed. Here we go. Correctly signed according to the operation. For division, when the divisor is 0 and the dividend is a finite non-zero number, the sign of the infinity is the exclusive OR of the operand signs. So there you go.
Got it.
We follow this. Let's go there. Let's go to that section because this section. Yeah, there's the thing that explains all the sign bit. Yeah. All right. So if you like, that's division by 0. So that's an exception case, and imagine that there's a little bit of code here. This here is the code that does division. It is mostly comments, and I'll go through the algorithm in a little bit because I think that's actually, it's kind of an interesting algorithm, and it illustrates some of the points that we're talking about. But what I want to show you is this. This down here is at least as much code. This stuff is the stuff that does division. This stuff down here is the stuff that does all of the IEEE compliance. So this is the case where either 0 is not where either x is not a finite number or y is not a finite number. So we look at the category of y, something divided by 0, that's got to be either infinity divided by 0 or nan divided by 0. And so those are the cases. We have to do different things in each case. If we're dividing by nan, we return a nan. If we're returning by infinity, well, a number divided by infinity is 0. That makes sense. But we do have to worry about the sign, I think. Yes, no, that should be negative yes, that's where we do the XOR of the two signs. So we XOR the two signs and do that correctly. We return -0 or +0. Nan divided by infinity divided by nan. Number divided by infinity, number divided by nan. The point of that I want to, it doesn't matter what all this is. I just looked at the spec and I think I got it all right. And look, to be honest, because I didn't spend a whole lot of time on this. But the point that I want to drum in here is that this is division. It is really, I mean, it's that line of code. It's those lines of code. It's this, which I'll explain later because this is very interesting, and it's that. So that is division. And this stuff down here is, hang on, oh, I've lost it. All right, so that stuff is division, and this stuff is compliance. Now, this isn't very much circuitry in an FPU, but in a software library, it's a lot of code. And it's just to get all of these cases correct. And if you have a look at the standard, that they often have lists here, like this is ATAN2, which we'll come to in a moment. Here are all the cases that ATAN2 has to cover. That's, you know, that's what it means to be compliant with the standard, is you need to get all these cases correctly. You need to get ATAN2 positive 0, negative 0, and ATAN2 negative 0, negative 0 has to return different values. It's just the way the spec is written. And what can you do? That's what it means to be compliant. And your C standard library or your C++ standard library has to be compliant. Otherwise, it's not implementing the IEEE standard. And that means it's got to get all of these edge cases right. And that's really what I wanted to show everyone with is that. I wrote this so you don't have to. So unless you get the job of writing a compiler's standard library, you will not have to worry about any of this, because for kind of handmade hero kind of code, this is this is why we hire numerical analysts. I'm not a numeric analyst, but this is kind of why we hire them, is partly to get these cases correct, as well as to get the normal cases correct. All right, so. I'm not going to ask if there are any questions about this, because I don't want any questions about this. Let's talk about the actual division algorithm.
Yes.
Okay. So to divide x by y, we do. Now, I'm using doubles. And the reason is this is actually the algorithm not used modification, which is this part here. But that's I did this so that I didn't have to do it the way that real FPU do it. And part of the reason why I want to do this is so that you can actually see this is a real algorithm. This is what your FPU does when you ask for one floating point number divided by another floating point number. So the first obvious case here is extract exponent, because once again, if you have m1 times 2 to the e1 divided by m2 times 2 to the E2, then that equals M1 divided by M2 times 2 to the power of E1 minus E2. Once again, reduction. We're doing it so that now we only have to deal with numbers in the range from 1 to 2. Everything else is taken care of by this exponent extraction. So that's the first step. Here we go, the exponent of the result. Okay, now what this is, and I will explain how we get these in a minute. This is an approximation to 1 on y. It's a polynomial. This is using Horner's rule. So this is, if you like, it's for some 0 to 1 times x times x times x plus b3 times x times x times x, etc., etc. It only goes up to b4 anyway. I could have just included that. But the way we do it is by factoring out x in. If you like, there's a common factor of x here, so we just multiply this x times that. And then do the same there. This is the way we usually evaluate polynomials, because it usually causes the fewest numeric problems. It's not the only, and one thing that people, especially big AAA game programmers or people who write the sine and cosine library for console platforms, which are often different from the ones that you see in most C standard libraries, they don't like this because this is very serial. You've got the result of, like, you have to evaluation before do that multiplication before you can do this addition, and so on. And so it's long chain of data dependencies here. And a lot of kind of the big AAA game programmers do not like this. There is a related method that we may talk about if we have time. Otherwise, we might have to do this again. And we'll talk about one way to get around that serial, that big serial calculation. Anyway, so what this is these are the coefficients of the polynomial, and this is a polynomial approximation of 1 on y in the range 1 to 2. These numbers look magic. They're not magic. They're just sufficiently advanced technology. But it gives about 11 bits of accuracy within 0.01. Try it if you don't believe me. The code will be on the, I'll put it on the wiki or something, and you can try it for yourself. But I will explain how we get these numbers soon. This 11 bits of accuracy, I didn't pick that at random. Let me show you how I picked that. Whoops. Ooh, okay. Let me show you how I picked that. This is a document we've seen before. No, this one, that one. This is a document we've seen before, which is the Intel Software Developers Manual. I'm sure that this has turned up on the stream before. I seem to remember it.
Oh, yes.
If you search for reciprocal, what you find is there is an instruction. Here we go. Oops. Okay, let me try and find. Here we go. It's reciprocal. Here we go. An instruction called compute reciprocal of scalar single precision floating values, which is a slight lie. It isn't the reciprocal of a certain value. What it is an approximate reciprocal, which is good to around 1.5 times 10 to the minus 12. So no, I did not pick this 11 bits at random. This is what this instruction gives. And what this actually does is what the FPU is actually doing is it's actually using a lookup table. Because, you know, modern CPUs, we can waste lots of transistors on a ROM. And so inside the FPU, it doesn't use a polynomial approximation like this for the division operation. It uses this approximation that's based on a lookup table. Table is available. Intel very kindly gave us you'll make aware of, which is the approximate square root.
You may have to back up about 15 seconds there. Intel gave us what?
It gave us basically an instruction which accesses that lookup table.
Ah, okay, yes, gotcha.
Because it needs it anyway. Sometimes you need a reciprocal to 11 bits of precision. Computing a lighting calculation, even in high definition, was it a high dynamic range? That's actually only about 12 bits, I think. So a reciprocal that's less than 1.5 times 10 to the minus 12 might be good enough. So it is a handy instruction to have around. And same with reciprocal of square root. Once again, the mere existence of this instruction actually gives you a clue to how it's being implemented inside. The fact that it gives you an approximate reciprocal square root instead of an approximate square root to what algorithm the FPU is using to calculate square roots. I'm not going to go into them. I do happen to know what it is. Goldschmidt's algorithm. This is Goldschmidt's division algorithm. That's Goldschmidt's square root algorithm.
I see.
Yeah, and the one of the nice things about this is that the inner loop of the square root algorithm it uses is 3 uses of the same circuit. So you only have to implement one kind of circuit to implement square root. That's its key advantage there. Similarly here, all we do is multiplication, as we will see. I know that just looks like a subtraction, but wait, I will show you. Okay, so what we have here is we have a number. So we've now decided that we've got n divided by d, numerator divided by denominator, where we know denominator is in the range between 1 and 2. So we can use this to get 11 bits of precision on an approximation to 1 on d in this case. And so we can multiply both the numerator and the denominator by this number. And what that will give us is it will give us a new numerator, we'll call it n0, divided by d0, where d0 is 1 plus small number. 11, 0.001, a small number. Now, if we multiply this number by 2 minus d0, so 2 minus d0 times d0 is 1 plus e times 2 minus 1 plus e equals 1 plus e times 1 minus e, which equals 1 minus e squared. We know that e is a small number, less than 0.001, probably good to about 11 bits. So this is within 20, so this is 1 in 1,000. This is within 1 in a million of 1. If we do this twice, and this is what we're doing here, we actually do that twice. We multiply both the numerator 2 minus the denominator from the previous step. We get a number that's close enough to 1 that it's 1. And so that's how division works. Is you multiply both the numerator and the denominator by 2 minus the denominator twice. We don't actually have to do the second one because we don't care about the denominator. We know that's close to 1, and so the numerator is then x divided by y, and then we just put the exponent back, set the sign bit. So we did some sign hackery up there so that we know it's between 1 and 2, not -1 and -2. And that division works. So straightforward. Or do I need to go over that again?
That seems pretty straightforward, at least to me. Yeah. I will double check for questions, but okay. Again, I think the only part that is needs explanation is the part you were going to go into about how the magic constants are picked. For that part, but
Sure. The final thing that I'll talk about, and this is just really quick, is this 2 minus the denominator. The FPU doesn't actually do that. What it does is it has a trick that you can do if you've got lots of extra precision, like you're using a double to calculate floats. You don't actually need to do 2 minus denominator. And the reason is, if you have a number like, let's suppose that the denominator is less than 0. Let's say it's 0.110, okay, something like that. We want 2 minus that. So that's 2 minus, right? That's 2 in binary. Minus that. Now, I just picked this number at random, but I can tell you exactly what it is. It's 1.00110101. 0, 1, 0, 1. I didn't have to think very hard about that for reasons that will become clear at the moment. What this number is this number with all its bits flipped, and then adding a 1 to the last place. So that's the 2's complement. 2 minus that number is the 2's complement of that number. This last little add a 1 operation is so small that we don't care. We're using lots of extra bits of precision to calculate this. So rather than 2 minus 0, what it actually uses is not d0. Flip like that. So that's that the FPU does that we can't really do here. I mean, I guess we could, but it doesn't matter. Anyway. Yeah. Anyway, that's the division operation. So let's insight into how your FPU works. All right. Okay. So that's so now we're not going to worry about all of this from now on. We're just going to look at actually how we do things like get approximations like this. Let me just make sure that is in fact the next thing on the agenda. Yes. Okay. So that is how to come up with polynomial explanations for things, and this is, I think, where we start getting out of bit hackery and start talking maths. So I'm on a bit firm ground here. So one, you may be familiar from high school maths with Taylor series and Maclaurin series, where to Maclaurin series is that f of x equals f of 0 plus x x times 0, where this is the derivative, x squared on 2 factorial second derivative of 0 plus dot 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 dot. And this is an equality. This is actually for any sufficiently well-behaved function x, this is actually an equality. This is equal. If you add up all the infinite number of terms on the right, you get a function that is f, at least around the point 0. You can also do it around a different point by saying x minus, is it x plus a? Yeah, I think it's x plus a is f of a, prime of a, or is it x minus a? I can never remember. Doesn't matter anyway, because we're not going to use this. The important point is that it's either plus or minus a. It's just warning here. Don't make me do this. So the thing is that this is actually a good way to approximate a function at a point. But we don't actually want to approximate a function at a point. We want to approximate it over a range. So in this case, for example, we want an approximation to 1 on y that's good in the range from 1 to 2, not at the point 1.5. What we really want is a polynomial that gives that's known as the minimax polynomial, that it minimizes the maximum error over that range. And there's a mathematician named Chebyshev. He was a 19th century Russian mathematician who went into this problem, and he came up with a bunch of very interesting theory about this, most of which is not important. But one of the things that he showed is that the minimax polynomial, if it exists, has some very interesting properties. Now I'm going to use Mathematica here because I have a copy. So this is going to be easier than trying to write out maths and also do some of these calculations. So let's function approximations. That's how you load it? No, that's not how you load it. How do you load this? I'm just teaching myself
my Mathematica syntax is so rusty. I cannot remember anything. It's been like 10 years since I've used it.
Yeah, exactly. All right, what do we got here? Here we go. There we go. This is why we have Google, so we don't have to remember things. All right. Minimax approximation. Yeah, details. Approximate. Okay, that'll do. This is the verbose way of saying it, but that's all right. Okay. Now let me. There we go. It'll be a little bit easier to see it here. Do I have it now, or do I have to put a dot at the end? I think I'm right. Okay, good. So in this case, if we plot 1 on x, all right, we'll have to deal with a small font, I think. From x from 1 to 2, that's what the function looks like in that range. I think that's big enough, I assume.
Yes. Sorry
to anyone who's streaming from Australia in low def, as I often have to do. Sorry about that. Okay, so that's what the function looks like in that range. Calculate the minimax approximation. Let's get this, because you don't have to remember the syntax this way, from x from 1 to 2, and in order, what polynomial did I say? That's quartic, so 4, 0. The reason for this 0 is that this will actually calculate rational.
Can you say that one more time?
Then,
I think the
right,
alt tabbing, of course, made it so that we couldn't possibly hear the explanation. It only had bandwidth for one or the other.
So the reason for this 0 here is that this will calculate a rational approximation, so a polynomial divided by a polynomial. sometimes that's a better approximation than the polynomial, even for numeric analysis. If a function is very well approximated by use a rational approximation and pay for the division. All right, so we have this now. Lambda. Whoops. So there's our approximation there. And what you'll find is that is exactly that. So that's how I got that. I just used Mathematica. I will explain the algorithm to do this in a minute, but I just want to show you, because this is a minimax approximation, I want to show you a very interesting property of it, which is that now minimax approximation actually minimizes the relative error rather than the absolute error. So yeah, I'm slightly cheating a little bit here. So, but if we plot
could you explain what you mean by relative versus absolute error?
Okay, so so the absolute error is, if you like, a minus b, whereas the relative error is a minus b divided by magnitude of a or b. So if you like, it's the absolute error might be it's good to within 0.001, whereas an absolute error might be it's good to within 0.1.
Yep.
Relative error. The reason why relative error is sometimes a more useful thing is because these floating point numbers really are kind of relative.
Yes.
That value epsilon is the smallest number such that 1 plus epsilon is not equal to epsilon. Similarly, 2 epsilon is the smallest number such that 2 plus 2 epsilon is not equal to 2. And so the relative errors in floating point arithmetic scale like that.
Yep.
And so that's kind of the reason why. So this is the relative error between this polynomial and 1 on x in the range 1 to 2, I think. Yes. What the error function looks like. As you can see, it's within 0.003. So maybe I was lying about it being good to within 0.001. I'll change it. There we go. It's to within 0.003. Oh no, it's 0.003.
Yeah, I was gonna say it's better
right.
than you said it was.
Yeah. So what I want you to see, this is the difference between the approximation or approximate, okay? And this is oscillation. In fact, the theorem behind this is the Chebyshev's equi-oscillation theorem. That's what it's usually known as. And the point of it is that this function oscillates around 0, but also that the peaks have the same magnitude. That is, it hits this somewhere around, it's actually, here it is, it's 0.00029735. That's the actual number that's calculated there. That it hits that number there, then negative that number, then that number, then negative that number, then that number, then negative that number. And so the errors, same magnitude, and they alternate in sign. And this is a really interesting property. It kind of makes sense when you think about it. If one of these peaks was a little higher or a little lower, that would probably mean we haven't quite optimized it correctly. Mm-hmm. But it's this equi-oscillation property that actually, it turns out, helps us to find the minimax polynomial, because instead of trying to find the minimax polynomial, what we do is we try and look for an error function that looks like this. Now, just as a little aside, the name Chebyshev may be familiar to some people. You may have heard of Chebyshev polynomials, Chebyshev approximation, and so forth. He worked a lot on this. One of the things that's going to come up in a minute is what I'm going to call the Chebyshev nodes. And I'm just going to briefly explain what that is. Because there's another little feature of this that is not part of the equi-oscillation theorem, but it is kind of important. And that's that the places where this crosses the zero axis, cross this axis, they get closer together the further towards the ends of the interval you see. So these two roots, the places where it crosses the x-axis, are closer together than those. So if you, and this extends further. So if I come up with a degree 15 approximation, nope, might have to bump up the working precision to, there we go, 100 digits. There we go. So there we go. There's an order 15 polynomial that's good to 100 decimal places. And if I say P2x, I'm probably not using mathematical will here. And now if I plot the difference there between that and P2, maybe that was not a good example. Let's use something like that. You can see I'm very well prepared for this. Let's come up with order 7.
Well, the rule on Handmade Hero is people have to work through things on the stream, so you're not supposed to be well prepared.
Absolutely. Okay, so this approximation is good to 1.5 times 10 to the minus 6. Awesome. And now we'll plot that there, and we'll see. Okay, so there you go. So once again, you can see the distance between these two roots here is larger than the distance between these, which is larger than the distance here, and larger than the distance here. So this crosses the axis, and also, of course, the distance between these peaks. It gets smaller as you get towards the ends of the range. Now, to explain what they are that he came up with to help in his approximation theory. Let me show you something a little magic. So this is the error curve between a function that's a polynomial and the function that's not a polynomial. 1 on x is not a polynomial of finite degree. I'm going to plot this as the Chebyshev functions built in magically. So that's 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to use the order 8 polynomial x in the range x negative 1 to 1. So this is a set of polynomials that Chebyshev came up with. They have nothing to do with 1 on x whatsoever. This is a polynomial similar.
I think came up with these can you go back about 15 seconds there? I missed that last part. It was dropping out.
So this is a set of polynomials that he came up with. There's one for every order. So this is the 8th degree polynomial. I'll tell you how they're defined. There's 1 is the first one. That's the order 0 polynomial. The second one is x. So that's, if you like, T0x. So that's and then T1 of x is 1. Then Tn plus 1 of x is 2Tn minus T of n minus 1. No, x. I forgot there's an x there. So these are how they're defined. They are also equals a cos n cos x. That doesn't look like a polynomial, but trust me, it's a polynomial. It's I'm bringing this up so that this arc cos doesn't seem like magic to come up to it in the middle. And these polynomials, as it turns out, tend to approximate these error curves very well. This is in the range negative 1 to 1. That's just standard range, whereas this is in the range 1 to 2, which is the range we care about. And so we can start looking for an error function of this kind by starting with the polynomial that looks like this. And that gives us a looking. But the way it actually works is an algorithm. It's called algorithm. And the idea is...
I missed the name there. What was it again?
Remez. I checked. Okay. It is Remez. It's not Remeth or something like that. Now let me just see if I can... I've got the example here. Yeah, here we go. So if we have an initial guess as to where these peaks are, right? Let's say they're at x0, x1, x2, x3, blah, 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 blah. And what we can do is set up a linear system, a system of equations that looks like this. Here we go. So a0 plus a1x0 plus, that's correct, isn't it? Yes. a2x0 plus blah, blah, plus e equals f of x0, where f is the function that we're trying to find an approximation to. So what we're saying is that this polynomial, let's looking for a cubic, plus a3x0 cubed, that the error between this polynomial and the actual function is equal to e at that point, right? That we've found this point, we'll say we've found this point x0, which is this point where the extrema, and the error between, oh, sorry, this one here, they look so similar, that the difference between the function that we're trying to calculate and the polynomial approximation is exactly equal to e. And then at the next point, x1, the error is minus e, because it's the same magnitude and the opposite sign. And then we just keep going for the next one, and that's plus e, because the next one is the next sign. And, oh, sorry, these are the x1, x2. And then this gives us a linear system, because we know what these x0, x1, x2 are our initial guesses.
Right.
And then this gives this is okay. So x0 we know, x0 to the 3 is just a number. So this gives us a system of linear equations that are unknown in a0, a1, a2, a3, and e. And if we solve that system, we get an approximate polynomial, because these are the coefficients of the polynomial, and an estimate of the error. And if you have a look at the minimax polynomial here, one of the things that it does is this. What the outputs are, I'll give you a smaller one here. These are the points where it thought that the extrema were, these points here. Here's the polynomial, and here's e. So one of the things Mathematica is giving you is it's giving you the points where the extrema are. Notice one of them is 1 and one of them is 2. They are typically the ends of the range of the extrema points. It's giving you the polynomial, and it's also giving you the error, because that is the maximum error. It not only gives you the polynomial, it also gives you the approximation. So once you've done that, that gives you a polynomial. Then what you can do is you can say, okay, let's assume that that is the minimax polynomial, and we'll find the extrema points. So we'll actually subtract that polynomial from f and find the point that differs the most, and then use that as a next approximation to go through the loop again and solve this system again. And for behaved functions, this gives you the minimax polynomial if you iterate enough times. Now, this is a very tricky thing to get your head around, I think. Should we stop here and get some questions on this?
I think I would
sure
probably have a question to ask there, actually. So my question is just, starting with your initial guesses, I have seen that sort of thing before, obviously, where, it's like, okay, so you try to make some initial guesses, and if it's an algorithm that's about convergence, then typically, there's ways of trying to do good initial guesses and stuff like this. But so that part, I'm sure, is a sort of a separate issue. But once you start this process, I put the initial guesses in for my locations of the extremum. So that's x0, x1, x2, correct?
Okay, you lagged out at just the wrong point. Then you'll need to repeat that question. I'm sorry.
So my initial guesses are the zero crossings. X0, x1, x2 are zero crossings.
Yes. No, it's actually the
extrema. Okay, it's extreme. But let me. Okay, so that does require a little explanation. Okay.
So if I show, so that's the that's the eighth order Chebyshev polynomial. Let me show you what the ninth order polynomial looks like. The place where this crosses the zero axis is the extremum of this polynomial. And the place where this crosses the x-axis is the next extremum of this polynomial.
I see.
And
Okay.
it's really not obvious here.
Yep.
But if you want one nice property of these polynomials that Chebyshev defined, in theory, and it actually does quite well to just not bother with this iterative thing and just try and approximate it with a bunch of Chebyshev polynomials added together. And that actually, a lot of older numerical analysis textbooks just tell you to do that.
Okay.
And then they tell you, okay, now let's just add the next order approximation and then, but approximate with operation of this remedy.
That mostly cut out, unfortunately. Man, this link is awful. I'm so surprised at how tough it is to talk to Australia.
I'm sorry, it's perils of a different hemisphere.
It's true.
I could rant about this at length, but you probably wouldn't hear most of it, so let's not.
Well, also, the thing is ridiculous that Google's, like, I never understand why chat programs don't just buffer up what you say and then send it losslessly with error correction. Like, I can wait to hear what you have to say if I could hear it correctly, but instead they prioritize real time, which I don't care about that, you know?
Exactly. I guess for video conferencing or something like that, it makes sense.
Even so, what is it? It's not worth it if I can't understand you, right? You failed at the primary task in service of some secondary thing. Okay.
I'd like to point out, by the way, that this is home internet we're talking about here. When I'm actually at work, I work at a university, the University of Melbourne. The internet there is fabulous.
Okay.
Because it's designed for, high bandwidth research.
Yes.
And so this is why you never see me stream. This is why my streams have been historically silent for those who remember. The few times I stream is because it's just not worth it.
So, okay, let me ask my other question now then, because I just wanted to get that clarified because I wasn't sure which one it was. So my other question is, for the iteration, I'm not sure I quite understand. So you're saying that you switch. So once I do one initial guess, I linearly solve for A, and then I plug the A's back in as my new X's?
No.
Okay, so I missed that part. I didn't get.
Okay. All right. What you need to do then is you need to find the real points where this polynomial okay, so you've done that. You've done one iteration. You've now got this function.
Yes.
You've now got this p of x. You've now got this polynomial approximation to f.
Yes.
But of course, it's not equal to. Even if it's an approximation, it's not equal to. So there's some error function ex equals p of x minus f of x. Right? Mm-hmm. Where this is, again, it's a real function. It's not a polynomial. This is your polynomial. What you now do is you search this function extreme points. And that requires typically some kind of search on f. The easiest way to do it is to find the places where it crosses the x-axis. Again, because it's just the roots of this function. You can use like Newton-Raphson method or something to find the zeros, and then between those zeros you're going to find a maximum or a minimum.
Yes. Okay.
If it's well behaved, you can do it by fitting parabolas. There's a really nice algorithm which I'm going to introduce everyone to now, which is called golden section search, which is a very high precision, high quality one, and lots of people do this for when they need to do YouTube videos explaining it. But golden section search is a technique for finding a minimum or maximum of a strictly unimodal function. So this error function is going to be unimodal. It's going to be, it's going to be like shaped like a loop like this or a loop like this, between two roots of the function.
Yeah,
so it is unimodal in that range, and so you can use golden section search if you want to do something really, really principled. And look, there's even code in Python there if you want to code in Python.
There you go.
Okay, there you go. So there you go. Golden section search is a good way of doing that, or you can use the other way you can do it is by fitting parabolas, right? You can fit a parabola to this function, find the extremum, and then say, okay, use that as a refinement to fit another parabola. I'm not going to explain that, but
I understand.
for completeness, for section search is a really nice function to know about.
Okay.
Quite a lot, especially if you've got like a weird golden section search is often a really principled way of doing that. It's a very good way of doing it. All right. So that's the basic idea. It's the Remez exchange algorithm, and by iterating that enough times, you do get a minimax approximation, and that is pretty much. But as I said, I just use Mathematica because I'm lazy. I have actually the Remez exchange algorithm. I've got the source code sitting around using the GNU multi-precision library. And the reason why I'm not showing you the source code is the GNU multi-precision library is pretty horrible. Okay. Actually, no. Yeah, it's ugly work, but someone's got to do with it.
Okay.
I wouldn't deploy code using it, but to calculate constants that you deploy, I'm very happy to.
Okay.
All right. So that's polynomial approximation. There's a lot more that can be said about that, and we're not going to say it here. The important thing that I wanted to show you is that those numbers, they don't come from sufficiently advanced technology. All right. So that's that. And now it's signing side down. So we're getting there to the actual replacing the functions that we've got. Now let me just have a look at my notes just so that I don't lose track of. Okay, so what we want to do. The sine function, you know what sine looks like. Sine x in the range -10 to 10. Whoops, x -10 to 10. It looks like it repeats itself, and the period of the repeat, the distance between that and that, be where you get another copy of it, is 2 pi. So what we kind of want to do is we want to divide by 2 pi and take the remainder. And that reduces the range from there to there, so we only have to deal with numbers in that range, or maybe from -pi to pi would be a useful range as well. And in fact, -pi to pi is the one that I chose. The trouble is that pi is a transcendental number. It does not exact operation. Sorry, it doesn't exact representation in floating point. But conceptually, what we want to do is this. We want to take x, multiply it by 1 over 2 pi, whatever number that is, truncate it to an integer, and that gives us like the x divided by 2 pi. And then we want to take the remainder. We take x, subtract n times 2 pi, and that gives us a number in the range 0 to 2 pi. So that's all right, but the problem is that there are a couple of problems. One of them is, what if x is large? Now, obviously, a real implementation of sine and cosine, one for the, well, no, this is real, but one for the C standard library will have to deal with numbers up to the range 2 to the 1/6 or whatever it is, and we don't want to do that. We can deal with x in a much more limited range than that. We've got this truncation to an integer, which is actually a more expensive operation than you might think, and there are ways around that. But we've also got the problem that where you've got x, where x is close to a multiple of 2 pi, let's say it's somewhere around 2 pi, what you're subtracting is two numbers that are almost, and this catastrophic cancellation, which that's terrible, I know, but it's not going to actually, it's not actually a natural disaster. It's what happens is that you've got two mantisses that are almost equal, and when you subtract them, what you end up with is not bits. The way around and to get a number that's higher precision is we can actually split 2 pi up. Now again, I've multiplied by again I've got some constants here. Let me tell you what they are. Here they are. Here's 2 constants. Whoops. 6 point, so 2 pi is, what's 2 pi? 2 times pi. Whoops. You. Express as, hang on. Okay, let me just, n of that to, no, there we go. Okay, so it's 6.28319-ish. What I've done is I've split this up into 2 numbers. One of them is 6.2382, and the other one is negative that. This number is not special. This is 2 pi minus this number. But this number is special because it looks like it's close to 2 pi, but it has this representation in its bit pattern. And the thing that I want you to see is all these zeros at the end. I designed this constant that has 12 zeros at the end of the significand field. And that means that we can multiply this by a number integer up to 3-ish, 20, that's a power of 2.
Sorry, I missed that
that's
little
right.
last.
We can multiply this.
Missed that last part. Thanks to the internet fabulousness.
We can multiply this by a number by 1024, because 1024 is just manipulating exponent. Anything lower than that, we've got these to work with. Any number up to 1000, any integer up to 1024, this multiplication gives an exact result. Okay. So you can multiply this number by 999. And the number that you get is exact. You can divide it by 999 again, and you'll get exactly this number.
Okay.
This number is 2 pi minus k1. And this gives you, like, this is, I don't know, 12 in here. This is 23 bits of precision on the number 2 pi.
Okay.
Which is more than a single floating point number.
Yep.
Single precision. Okay. And then what we do is we just do reduced x equals x minus n times k1 minus n times k2. And that gives you x reduced into this range, 0 to pi or whatever it is, to a higher precision than you would get by multiplying by 2 pi at the cost of another multiply and a subtract.
And n, we're going to find n using a divide at some point or something?
We are going to use it. Okay, so what we're doing here is we're multiplying it by 1 over 2 pi. If you look at timings or something, you'll see multiplication divisions are slower, but because we saw the division algorithm, it uses a lot of multiplications.
Yes.
So you shouldn't run away from divisions screaming, but if we can do it without divisions, all the better. Okay. Now here's the next thing, which is how we actually find n, because it's interesting as well. I've got this number, which is 1.5 divided by epsilon. This is a large number. Remember, R32 epsilon is a small number. It's 10 to the minus or something. So 1.5 divided by that is a large number. This is an exact number, of course. This is 2 to the minus 23. So this is 1.5 times 2 to the power of 23. So it's a reasonably big number. But it's a number that has this really interesting feature that if you take a number like x times 1 over 2 pi, add that number and then subtract that number, it has the effect of rounding this value to an integer, as long as this addition and subtraction will fit. So this will only work for x in a certain range, but we're saying this work up to 1,000. As I said earlier, a C standard library implementation has to work over the whole range of numbers, and so it will special case this a lot. But up to 1,000 is probably good enough. It's probably not good enough for the audio thing you did really, really early on, that sine wave.
Right.
You probably don't want to use it for that. Because if it runs for long enough, it's really honest. But yeah, so don't do that. But for rotations, really, 1,000 radians is it's like 300 rotations of the circle.
Yeah, it should not.
Really don't need
you should not be up in that range, generally speaking.
Yeah. You should not be up not for games. No.
Yeah.
No. Okay, and so this has the effect of using the floating point unit to round this number to an integer. But it's an integer that's represented as a floating point number.
Yes.
And so that's how we do it. Now, the actual code is a little bit more complicated than that. So let's actually have a look at the implementation. No. Wait, I keep opening new editors every time I need something. Didn't do that. I alt-tabbed, so I'm going to be quiet for a second.
Some people on the stream were asking if you could turn the video bitrate down, but I don't know if that's actually possible any more than it already is.
Yeah, sorry. I can't.
Yeah, I didn't think so.
Yeah. Okay, so this is the actual code in the sine cosine table version that I implemented. So this the signature is it takes an x, a pointer to a sine x, and a pointer to a cosine x, and it stores sine and cosine in there. So here's that round to integer. Here's the range reduction, which I've actually used 3 constants for, and I will explain that in a minute. It turned out that I actually got a little bit more precision by splitting 2 pi into 3 constants. Okay. This K2 again has that property that if you multiply it by a number up to about 1,000, it's an exact representation. And there's that x times 1 over 2 pi plus round to integer minus round to integer, and then it does this down of range reduction using only K1 and K2. And then I use K3 here to adjust the answer. So this is x times. Okay, so this is the table lookup part, which we'll talk about in a minute, because this is the other, I think, thing about this code is that so this basically does that, rounding it to an integer here, and then we can use this here n, where n is a floating point number, and we don't have to do an integer and back again. All right. Now let's take a quick look at trigonometric identities, because we need to look at this. So again, this is probably high school maths. No, it wasn't high school maths for me, strangely enough. When I was in high school, we didn't really do trigonometric identities very much, but I understand it's
really?
part of the curriculum. Probably, yeah, no, really, which is interesting. But the thing is, I never remember them anyway, and you shouldn't. Yeah, and you shouldn't, because whenever I need a trigonometric identity, I derive it. And let me tell you how I derive it. There are 2 identities that I remember. One of them is this one, sine squared x. x plus cosine squared x equals 1. And I remember because it's Pythagoras theorem.
Yep.
You have a right angled triangle with a 1 on the hypotenuse. It is so you should be memorize that one. Please memorize that one.
Yep.
The other one that I memorize is this one, is that x equals cosine x plus I sine x, where I squared equals -1. So if I is a -1, not the square root of -1, please don't make that mistake, it annoys people, then e to the power of ix is cosine x plus I sine of x. And this is Euler's, Euler, E-U-L-E-R. Euler and Gauss have so many things named after them. You can be forgiven for just saying, oh yes, that's you're probably right. You're probably 50% chance of being right if you name one of those two, in this kind of entry function arithmetic especially. All right, so now the way this is, suppose you want to know what cosine of a plus b is. So I don't identity, because if I do this plus I times sine of a plus b, then this is equal to e to the power of a plus b. Okay, that's just that identity applied. That's x is e to the power of here. Let me do that, because that's everyone knows that x is e to the power of, right?
Yes.
The e is Euler's constant 2.71828, blah blah blah. Yep. Base of natural logarithms. Okay, this is equal to e to the ia times e to the ib. Okay, that's the index laws here and distributive law of that, which is equal to cosine of a plus I sine of a times cosine of b plus I sine b, which is equal to cosine a cos b minus sine a, because that's I sine b is negative multiplied by I, plus I times cos a sine b plus sine a cos b. And I'm going to put parentheses around here, because now we can match up the real and imaginary parts of that line and that line. And what we find is that sine of a plus b equals that, and sine of a plus b equals that. And there we go. They're identities. And this memorize another trigonometric identity again. So that's for anyone who's doing high school, American high school maths. So there we go. Okay. So what this gives us, these formulas, is it gives us, if we can calculate cosine a at a point a, cosine a and sine a at a point, then we can calculate values of cosine around a. So if instead of b we think of this as epsilon, small number, right? Then if we've got cosine of a and sine of a of a point, then this cosine of e and sine of e, if we can come up with a nice polynomial approximation that's good in a small around 0, this formula gives us a way to calculate cosine at a point around that value. And so we're using here. And by the way, the reason why I'm using this approach is that this code is branch free. And this is I read between the lines of the requirements that are much easier.
Say that one more time.
That is, if we want to calculate version, is going to be much easier to version. So calculate 4.
Can you say the part from read between the lines again? That was like, for some reason it dropped out pretty severely there, so I didn't really I couldn't quite reconstruct it.
Sure, I read between the lines on the requirements here. This before you sampling stuff. And I figured you probably want a version that you can do 4 sines and 4 cosines.
Yes, you're correct.
in a vector instructions. Yes.
Pretty much anything
Okay.
that you're going to do in a math library in a game these days wants to be able to
Yeah.
be done wide. And it can have branches, but you have to factor in the cost of those branches. Both branches will be taken. So usually it doesn't help you if one of, if you're doing a branch to save time, that really doesn't help you.
That's right. Now, I am trying a different approach down here, and I'm eventually going to get rid of these branches down here. But we'll just have a quick look at that moment. This is experimental code. It does not work. It's buggy. Do not use it.
Okay.
The only catch here is these dependent loads, is that this table lookup does require taking a number, converting it to an integer, and then reading a table. Now, the table is only that, and this in a couple of characters. So it's a small table. I'm not so concerned about the cost of the load. Getting rid of a floating point square root even, and if you floating point square root because it's expensive and you're replacing it with one cache miss, that's actually a bad trade-off.
Right.
So if you are using tables, you want to make them small, but this still is a dependent load here.
Yeah.
So I'm going to defer to your expertise on making this into a vector. With it if you want, but something for. Okay. So what we've got here is this table is. This is a value of x. This is sine of x, and this is cosine of x at various sample points. What I decided to do was I originally tried using these sample points. So what we do is we sample sine and cosine at a bunch of points, and then we use a polynomial approximation for sine and cosine using Mathematica, using exactly what we've discussed, to calculate sine and cosine in a smaller range. So I originally used integers, now using half integers because it improves things enormously. The table for integers fits in a cache line, which is very nice. It fits in 2 cache lines. I think it's an acceptable trade-off. If we sample them, we're sampling them in the range negative pi to pi because this range reduction algorithm gives us a value in that range. So I'm sampling it at -3, -3.5, 2.5, -2, -1.5, 1, 5, blah, blah, blah. So these are the points that I'm sampling them at. And I say sort of because it's actually not quite. The reasons that will become clear in a moment. So that's the reason for this multiply by 2 here. We're taking this value that we've done here, that we've got here, which is x range reduced from negative pi to pi, multiplying it by 2, rounding it to an integer again. Probably don't need to round it to an integer, actually. We can probably just do this. Yeah, in fact, let's do that. Let's keep that in case. That's probably fine. This 6 is just to do with the fact that arrays start at 0 in C. Mm-hmm. Counting starts at 0. Counting has always started at 0. Even before 0 was invented, counting started at 0. It's true. This is Wadler has a wonderful talk on this, explaining how counting has always started at 0.
Wait, who is
obvious
this?
Phil Wadler. He's one of them, probably the most cited computer scientist of all time. He has wonderful paper titles like Theorems for and all that sort of thing. Paper titles, but he has this wonderful talk on things obvious in retrospect. And one of them, things that's obvious in retrospect, is counting starts at 0.
Interesting.
So, yeah, exactly. Just a little aside there. Okay, but what you might notice here is this is the value of x we're looking at, and it's not exactly, and this is exactly negative 2.5. I've this in scientific notation, but so this is correct. And that's not exactly negative 2, and that's not exactly negative 1. Offset them slightly.
Yes.
And you can do this. Once you're thinking in terms of these tables, there's no reason why you actually have to sample at that point. And there are two reasons. First of all, there's a good reason for putting X in here. And that's so that this calculation doesn't have to be exact. If there's some round error in here, all that means is that we were close to 1.5 and we went slightly high instead of slightly low.
Gotcha.
But that's okay. If we just make these polynomial summations just a little wider, so they work over a slightly wider range than negative 5.5 to 0.5, we can compensate for that. That's the first reason. That's a good reason to put X in the table. But the other reason is once you've decided that you've put X in the table, it doesn't have to be exactly the center of the range. And again, I did not pick numbers at random. I picked them for a very careful reason. Let me just run it. I've actually got code, and this will be part of the thing which calculates these tables, calculate sine cos table, where we find sine and cosine somewhere around -3, somewhere around -2.5, somewhere around -1.5. And now, let me give you the example here. This is an actual result. This is 0.5. So this is what we get for 0.5. So instead of 0.5, we actually use that number, which is a few floating point numbers away from 0.5. And the reason why that one, the difference is 2 times 10 to the -6. So that's a very, very small number of radians. But the reason why is because sine and cosine have a property here. This is double precision, okay? Stuff we did earlier. This is sine of that number in all these zeros at the end.
Yep.
Yeah, I picked that number because it's close to that, but also it's got all these zeros at the end. And in particular, this number fits in a single precision float in a binary 32.
Got it.
So this is a double precision answer that fits in a good double precision. And so this number here is pretty close to exact, as is this one, as is this one, as is this one. These numbers are very close to exact.
I see.
And one a little bit more precision out of the value.
Gotcha.
Now, so this involves searching floating point numbers. And again, I did not implement this in a handmade kind of way. I used the C standard library for this. But there's a little function that not many people know about. It's in math.h. There's actually a family of functions. Well, one of them is next after, and the other one is next toward. And what is next after f of x plus 100, random number. This gives you the next floating point number after x in the direction of x plus 100.
Okay.
So using this technique, what we can do is we can search adjacent floating point numbers. So in this case, what I've done is I've said we'll search 100 floating point numbers in each direction. And what we want is the best one. That is, we want one with the most zeros after the real 32 mantissa.
Got it.
So if you like, we go up to the end of the mantissa of a single precision float, then we count the zeros following, and we want the one with the most. And in the case of ties, we want the one that's closest. That's closest. We're looking for. What these loops do, they calculate sine and cosine in double precision using the library because high quality to be. And it's slow as well. It's not what we want for Handmade Hero, but it's fine for general purpose. And then we calculate that, we count the zeros after it. So I've replicated some of this real 32 stuff in real 64 here. There's the union for it.
Got it.
Because I need to work with doubles. And then here's the thing that counts the zeros after real 32. I just did it as I think I just did it as a loop. Yeah, I just did it as a loop. You know, again, if this was speed we cared about, we'd use bit scan reverse or something. And again, to handle the subnormal case, we use 2 to the 55 instead of 2 to the 23, which we used in the previous example. We don't adjust the exponent for that because we don't care about the exponent. We're just looking for zeros in the mantissa. And that's basically all we do. The code is actually quite straightforward once you understand the bit hackery that's going on here. And so that's how we calculate those sine and cosine tables. And then the only thing left is this is a polynomial approximation to cosine. This is a polynomial approximation to sine. And this is a slightly rearranged polynomial evaluation with some, you know, we share some of it here, but it is essentially the same thing that's going on. It's just rearranged a little bit for precision, so that the most important terms are added on at the end here. And the other thing is, of course, this third constant, K3, that we split 2 pi into, we just added on to XD here. And that way, it doesn't have to go through this rigmarole. We preserve these very small error compensation term, and we just add it into XD here, and that's the argument of the polynomials. That was a long speech by me. Is there anything that anyone did not follow there?
So I have a couple questions I can ask. Yeah. So my first question is, can you go back to the table there? Because so the thing that I'm sure if I looked at the code more carefully, I would probably understand. But
yeah,
you've got 2 terms coming out of the table, but then you've got a bunch of terms that are the same no matter where you are in the table. How can you add a little more exposition there to why part of it looks up the table, part of it's the same no matter where you are?
Do you mean like that? Do you mean that some of these table entries are the same? Is that the question that you're asking?
No.
Or
what I meant was, so to look up into the table, you're getting back some part of the computation going forward, but then no matter where you were when you looked up your base point in the table, the polynomial terms don't have to get looked up in the table. Those are the same everywhere. And I was just...
That's correct. Yeah.
Until I look at it more closely,
right.
I wouldn't be able to figure out why that was. So I was wondering if you could explain that part a little bit.
Okay. Sure. So what you're doing is you're looking up cosine of a plus e, where a is a point that's sampled in the table.
Right.
So cosine a and sine a are stored in the table.
Right.
Cosine e and sine e are the polynomial approximations.
Okay, right. And they're going to be the same because you're always around 0 at that point.
They're around 0 at that point, right? We take to work out the argument for the polynomial, we take x prime, which is x that's been range reduced, subtract x in the table, and that makes it between roughly negative 0.5 and 0.5.
Yep.
And then this little error compensation term.
Got it.
That. And so the reason why this xd here is always in the range somewhere around negative 0.5 to somewhere around positive 0.5.
Got it.
It is slightly wider because I did actually, I put the difference between x and the sample point here, and I took the maximum of those and expanded the range of that the polynomial is good at by that a little bit.
That makes sense.
And then I expanded it again by a number that's related to K3, because that error compensation term. So I was very, very careful about this.
Yes.
Again, these numbers are not magic. It's just that's the reason for that is and XD2 because these polynomials. This is things. There's 0 x to the 0, x to the 0 to the 6. This is always x to the 1, x to the 3, x to the 5, x to the 7. These are all odd values because it's centered around 0. That makes sense. We pre-calculate xd squared as well, just to save a bit of calculation later on. These are the right-hand sides of cosine and sine from C2 to C6. So that's a Horner's rule calculation there. You can actually see that looks like a polynomial evaluation. We just plug those in. But we take the first couple of polynomial evaluations and add them on at the end, just for that you sometimes can get an extra precision if you're just careful about the way you add those together.
Gotcha.
Again, it's not magic; it's just a little tricky. Yeah.
So
you can see there sine items. Yeah. Sorry.
So my other question would be, for if trying to do wide versions of these, it's very hard to do table lookups because each lane has to look up a different entry in the table typically. So what sort of stuff would you end up doing if you couldn't use a table?
Okay. So this is where this version comes in.
Okay.
So this is as I said, this is experimental code. Where what I'm doing here is doing range reducing instead of from the range negative pi. I'm range reducing range from 0 is that part of it. I'll show you. So the sine of x from 0 to is that, and the cosine is that, and these are just mirror images of each other.
Yes.
Because this and that are mirror images of each other, we should be able to evaluate it by simply using a different x, pi on 2 minus x.
Yes.
And then evaluating the same approximation there. Again, for this part of the range here, that shape there is the same as that shape there, only it's negative.
Yes.
This shape here is the same as this shape here, only it's a mirror image around that line. So the other way of doing it, and this is a common that you'll find, is to use this kind of quadrant analysis. You decide which part of this, no, that's a Chebyshev polynomial. It looks so much like a sine.
Yeah, that's kind of shockingly the same.
Yeah, exactly. This is the sine curve. This is one whole period. You split into quadrants. There's one quadrant here, one quadrant here, one quadrant here, and one quadrant here. And this is they only differ by flipping the sign of the answer and also kind of mirror imaging around kind of a line. Imagine a line drawn down there.
Yes.
So that's what I'm trying to do here. At the moment, I'm doing it with case analysis, and this case is buggy at the moment. And here's these negative sign adjusts here. What I eventually want to do is I want to turn this into bit hackery, so that we can do that part branch free, and then just do two polynomial evaluations. They use the same approximation because one of them is just the mirror image of each other, so that's okay. In theory, you could do both of these in using vector instructions, so that's nice. Or maybe you don't want to. If you want to calculate, 4 sines and cosines in parallel, maybe you just don't want to bother with that and just do those in parallel.
That's usually how it's done because
these are completely independent.
Usually you compute them in parallel because typically if you're in a performance-oriented scenario, packing and unpacking is just, you lose too much time. So they typically try to go like, all right, look, let's just process things in bulk. Yeah. So we're going to try and take 4 angles in and spit 4 values, well, 8 values, I guess, in this case out.
But also, of course, this is a sequential computation. It's data dependent, right? This C depends on that. Mm-hmm. This C depends on that. And so interleaving these two computations would probably help quite a lot as well.
Well, the CPU will do that for you automatically these days, of course.
Yeah, well, although that's a lot of instruction resource.
Yeah. I mean,
So you kind of,
But you said this
Yeah.
routine wasn't working yet. You have a big do not use on the top of it. So what haven't you done yet
That's
here? I'm
correct.
curious.
Okay, I haven't fully debugged this quadrant calculation here.
Ah.
There's, I mean, I can show you.
Hmm.
I can show you. So this is here. We've got at the start here the quadrant number. So in quadrant one, oh look, the difference is 5 times 10 to the minus 8, 0, 0. The difference between sine x is calculated by the C standard library and is calculated by this routine. The difference is 0, 10 to the minus. It's
I
good
see.
in that quadrant. But when you get to quadrant 3, you find that the difference is negative 3 times 10 to the minus 3, negative 1.4 times 10 to the minus 1. So
Yeah.
sine looks correct, but there's a bug in cosine, and I assume I've just got that wrong, or maybe I need to. I'm not sure. I'm not sure what I need to do there. It was like 11 o'clock at night. And I needed
Okay.
to go to bed.
Yes. Yes.
So I will work on that a little bit, and then my next step after that will be to turn this branch into bit hackery. So we'll
Yes.
try and do it with the compare instructions that are built into SSE and masking and whatever we need to do, and also of course this sine adjust here will be extract the sine bit, and then we'll put the sine bit back on the answer
Right.
instead of a bit hackery as well. So that's my theory with this, because I want to see which one performs better. Basically, this is going to involve, this will be bit hackery. It will be single line, it will be single thread branch free code. But my feeling is that it's going to be a lot of code, and probably comparable with one of these. That there'll be about as much code to calculate this as there will be to calculate one of these polynomials.
I see.
And I don't know if that is better than a table lookup or not. And there's only one way to find out.
Table lookups do tend to be pretty expensive just because you have to. It's really you have to extract, lookup, and repack. But
Yeah.
it's hard to say.
So
One of the things
yeah.
I think Fabian has often said is that he's often surprised at how often table lookups still win, though. Because like
Exactly.
the conventional wisdom is that like, oh, don't do a table lookup, just compute the value. But then he says oftentimes when he tries it, he finds that is not true.
Yeah, exactly. So who knows?
Yeah.
Who knows? And that's why I thought that for Handmade Hero, I think the right thing to do was to try it both ways.
Yeah, and we'll have to.
And also
help
because
with this,
these are the two ways floating point that your C standard library does it. The implementation of x2, for example, or ex or 2 to the x, it will use table lookup, whereas the implementation of sine and cosine probably doesn't. It probably uses this quadrant analysis and a high degree polynomial, probably even higher than that double precision. Might be degree 15 or something. I don't know.
Gotcha.
So your library does it both ways. So it's worth a try both ways to see what works. We'll probably be surprised because our requirements are very different from the C library. You've got to try one works.
Yeah.
And try it all ways and see. So
awesome.
Yeah, there's the debugging line that prints all that crap. Okay, so that's sine code. Look, somebody has probably already worked out the bug in this.
Probably not yet.
As long as we haven't lost them. All right. So that's that. Now the next thing is tangent. So before we go on to arctangent, maybe you could just see any questions, because it is getting it's been 2.5 hours.
If you want to, we can save Atan2 for a separate time. It's really up to you. The only questions that I see on here were about C0, C2, C4, C6, etc. Those constants that were used before. Someone was asking, do they have more precision than can fit in a float?
Oh yes, you're only. Well, I've written them here in more precision than will fit in a float, because this is what came straight out of Mathematica, and I
Right.
decided, yeah, I'll just dump it all here,
Right.
and the compiler will round that to a
For
floating
you.
point.
Yeah. Okay. But that was pretty much
So
it.
you only have about 7 digits of decimal precision in a floating point. I mean, these are bigger than they are as well. But if you just dump more digits than you need in there, calculate it with a double and put it in and stick a little f on the end,
Yes.
the compiler will round it to a float for you. And yeah.
All right.
Compilers are smart about that these days. Okay. So we'll have a quick look at A10-2. There is really two A10-2. This is mostly geometry. Now, this is. I'm not claiming that A10-2 is good. One of the things that I did a little secret stream a couple of weeks ago where I was writing A10-2, is we had a look at how Handmade Hero uses A10-2. Do you know how Handmade Hero uses A10-2?
So to be honest, I don't think we really use it yet in any meaningful way. I was only assuming we would eventually use it. We could get rid of it right now. I think it's just for like joystick direction or something stupid like that. I don't remember.
But it's even worse than that. It's not even joystick direction. It only returns one. It's only called with one of 4 arguments: the north, south, east, west.
Okay, so maybe we don't need to do A10-2.
Maybe we don't need to do A10-2, and maybe we'll talk about this as a future point. To prove that, again, most of A10-2 is quadrant analysis. And there is a certain amount of quadrant analysis that I do here. I'm using, this is a Weierstrass transformation. Maybe we will leave this for another time because of maths overload.
Yeah, I can just go remove A10-2 for now, and we can do another stream if I put it back for a legitimate purpose in the future.
Sure. I will say one thing. First of all, I do two things. First of all, I implement A10-2 in terms of A10. A10 here is using the techniques that we've been talking about. Is an order 15 polynomial here, because that's as much as I needed to get a good result.
Okay.
And there's also a range reduction. So the range reduction that we need to know here is if you look at arctan, if we plot that, arctan looks like this. Okay, so it maxes out at pi on 2 here and negative pi on 2 on here. But what's interesting is what happens in the range from negative 1 to 1. Okay? It looks like it's reasonably well behaved. It actually isn't. And one of the nasty things about A10 is that when you just try the Remez exchange algorithm, polynomial algorithm, that look really doesn't work so well on A10. A10 behaves really weirdly like this. So, once again, I just use Mathematica, but I have tried my implementation of the Remez exchange algorithm on A10, and it really doesn't work that well. It's very hard to get it to converge. So, got you there. So we'll just ignore that little wrinkle. I've got that will give me polynomial approximations. So it is magic now. That outside of 1 to 1, what you can use is you can use a useful little identity, which is A10 of 1 on x equals negative for x, where x is no. It's no. I tell a lie. It is it's pi on 2 minus A10 of x. This is x positive. And that's pretty much what we do here. We use the x is less than 1 case, x is less than 1, absolute x is greater than 1 case here, where we just do.
Okay.
And then adjust that. So that's how we get A10 over the whole range here. Implementations, once again, standard library implementations split the domain up into more parts than that. because this 15-degree polynomial is kind of but this works. However, the other thing I want to point out is for the cases that Handmade Hero uses atan2, that's that code there. So I can pretty much guarantee it will work because I've had special cases. I've had to special case those ones so we're getting zeros.
Okay.
The other I'll use here was so x and y, the hypotenuse. And the reason why I use a special function for that is that Pythagoras theorem. It's the square root of x squared plus y squared, except that x and y can overflow.
Okay.
It can overflow the value of x. And so this is the hypotenuse function up here. Again, I'll come up with a better one later, but that. All right, so I don't want to explain atan2 any further right at the moment because, as I said, Handmade Hero doesn't really use it at the moment. But the cases where it does use it are dealt with in this.
So I should probably go remove atan2 from the source code then, but sine and cosine we will definitely want. So
yes.
We'll have to start taking a look at that based on what you've done so far, which I thank you so much for coming on and explaining all that. That was very clear, actually. I feel like I have a pretty good idea about how that sort of stuff goes now, much more so than I did, certainly.
Good, glad to hear it. So let me just load up my chat here, and maybe we can go to Q&A now.
All right, let's take a look. I will put Q&A on here.
Yeah. Hello, InsertBot. Is anyone completely lost? Too much maths, sorry.
Who said that?
That was me.
Oh, okay.
Okay, if the values are denormal, they will run away slow. They will run way slower. Sorry, 0b0000, which is a denormal number. Thank you for having a denormal number as your username, by the way. Which cases are you talking about for which function? Okay, what was the reason we couldn't do 2's complement in the exponent? The reason why we don't do 2's complement as the exponent is so that if you have a bunch of zeros, you fill a block of memory with 0 bytes, and then you read that as a floating point number, you get the number 0. If you used 2's complement, then that would be an exponent of 2 to the 0, which is 1, and that is a very common case. So that's the reason why we don't use. That's the reason why we use the bias representation for the exponent. Is because programmers really, really like it. If 0, then read it as a number. It's 0. Okay, sine and cosine. All right. So, Mr. Ormer's denormal number for your username, sine and cosine. Yes, this is true. When for cosine, it's okay. This is the question here is essentially what happens if you are calculating the sine or cosine of a subnormal number. The cosine of a subnormal number is all right. It's close enough to 1. For sine of x, yes, you're right. You can just use x. But the reason why I don't want to do that is I don't want to introduce a branch. This is branch-free code by design, and we want to keep it that way for all of the reasons we've talked about. And yes, that means it's slightly imprecise around that range. So we can check to see if it's going to be too bad. There's a wonderful book I read once. This is let me see if I can find it. It's Basic Animation Stand Techniques. And this is a book from way, way back in the day of traditional animation. Yeah, that's the one. From 1977. And it was about using these multiplane animation cameras. It's basically a guide camera for traditional animation and stuff that these animation stands to actually animation. And it's got all of these knobs down here. I don't know if you can see these knobs that do things like rotate the camera and rotate the stand that it's on and all that sort of thing. And these really only give you precision to about 0.01 of a degree. And when you had to do pans and zooms and rotates and so forth, the animation stand operator would actually have to calculate all the sines and cosines, probably using tables or a slide rule or some combination thereof, and would calculate and basically can't see a rotation of less than 0.01 degrees. It's at 24 frames a second. It's impossible. Anything that's calculated to 0.01 degrees of precision looks smooth.
Can
okay.
I mention one thing in there too?
Posted. Yeah.
Yeah. So I guess I'm slightly
Yes.
confused as to the question in the first place, because I mean, at least in my experience, usually denormals you want to flush to zero anyway. Like a game never wants to be running with denormal, so it should never be asking for the cosine or sine of a denormal.
I think that will be true. Yeah.
So that was just kind of I just wanted to throw that out there, is that these routines shouldn't ever take denormals as inputs. It probably should have been flushed to zero long before it would ever get to this routine, and so just the specification for what these routines should do should not include denormals in general. It should neither accept nor output them generally.
Right. Cool. And the thing is, right, an angle of 2 to the minus 126 radians is not perceivable as a rotation. I guess that's my point. And that's the rule of thumb that they used to use. You know, this is an Oxbury animation stand. The Disney multiplane camera was similar. They really only work to 0.01 of a degree. Anything smaller than that is not really perceivable as a rotation.
Yes.
Yeah. Okay. All right. Unless you explicitly flush. Oh, they'll run super slow. Sorry. Oh, do you mean? Okay. So the question here is saying that if you actually supply a subnormal number to these routines, it will run slower.
Yes, and this is what I was. Right. I guess I failed to get this across, though. What I was saying is that in games we always turn on flush to zero, so you don't get denormal numbers.
Yeah. Okay.
In general, that's what I was kind of trying to get across, but I think I failed to do so.
Yeah. Sure. And this, by the way, to anyone watching along, this is the difference between a numeric analyst and a game programmer, right?
Yes, exactly.
I'm pretending to be a numeric analyst, and Casey is actually a game programmer, and this is the difference in thinking, I think. And you're absolutely right. For if we were implementing the C runtime libraries version of cosine and sine, we would deal with the subnormal case separately. We absolutely would. Is there a version of this math source code anywhere, or will be included in the Handmade project eventually? Both. So I'm releasing this under the MIT license so that Handmade Hero can use it, and I'm not sure how I'm going to release it. Maybe on GitHub, but the explanation is going on the wiki. But yeah, at the very least, I mean, people who have access to the Handmade Hero source code are obviously going to get it first, because Casey's probably going to incorporate it fairly soon.
Well, and also, again, this is just for educational purposes. There are many math libraries out there. You can go get implementations of sine and cosine and so on. The point of this was we wanted one that we had gone through so we can know how it works, and everyone's seen how you do one of them. The idea is not to give you a library that you're supposed to use for sine and cosine. It's, because there are many out there you could find.
This is exactly right. the GNU standard library is open source. The Apple is this at least older version. The trouble is, of course, you will never understand them if you look at them. This is really a look into how the sausage is made.
Yeah, and hopefully, if you followed that, and on stream, I'm gonna basically go and do an SSE implementation of equivalent routines. Now that we've gone through one of them, the idea is that once you know that, then if you do go use a library, or if you do want to make your own versions of sine and cosine for specific purposes, or try to make them faster, now you have sort of a basic understanding of what's going on, so you've got your footing there, as opposed to if we just grabbed something out of one of those math libraries, we would have no idea. We'd just be like, I don't know, like, who knows how they did it, because, again, if you haven't gone through it, you wouldn't know.
Yeah. Exactly. These constants are a case in point, right? These range reduction constants that we use in sine and cosine here, they you would never know where these came from if no one would explain them to you. I mean, maybe it's called a Cody weight reduction. If you want to look it up, that's its official name. I don't know who these guys were. I think it's from a textbook rather than a paper, but everyone who's done research, like, there are papers that formally prove these correct if you have a fused multiply add instruction and so forth, and it's all very fun and very important, and you don't really need to care about. But yes, Cody weight reduction is what you want to look up if you're curious about how that works. Will you go through only if we...
Yeah, our cosine, like the inverse cosine functions are not really useful to us that I know of in Handmade Hero, so we probably wouldn't be going over those.
Pseudonym 73. That is me. I'm beginning pretty much. I think I skipped most of the first week, which was Introduction to C, but I've been here every time that it's the stream time zone, and I've been around. So if you've been around, you probably know who I am by username.
Yeah.
Yeah.
Let's see. Any other ones? Looks like that's it. And I guess I'll try to bring up one thing really quickly here on my end. If I can find a quick reference to it, but otherwise we can go in there and so basically, I'll look this up on a different stream, but for the questioning about the d-normal numbers, in terms of the actual SIMD unit in the x64 processor that we're actually talking about, I just again want to emphasize the fact that the concern about d-normal numbers is more of an x87 FPU kind of a concern. Like, when you're programming in SSE, it's pretty easy to just make sure that you don't have to deal with d-normal numbers. That's not something that's really a problem with that. Not sure how to show that other than just to go over the architecture guide, but we can do that on another stream. I can show you in the architecture guide. D-normal numbers are not really an issue in that way. Like, the slow d-normal numbers thing used to be a problem on x87. It was something you had to think about more, but it's not really something you have to think about as much anymore.
Okay, and binary zero. I don't know how to pronounce your username. I can show you. I can show you some versions that are completely branchless without tables. If you're interested, sure, absolutely, very interested. Once again, this is not necessarily. I'm not necessarily telling you how to do it. I'm just telling you how I did it. And I do not claim that this is industrial strength for all applications, because that's here. And once again, this quadrant version, I intend to make this branch free without tables. So that will happen. But yes, if you've got a version that's completely branchless without tables, by all means, share. There's there on the Handmade network. There'll be a forum entry for this stream, I'm sure.
And also, someone was asking, have we done speed comparisons versus the C versions? Also, again, that was not really the point here. This is not an optimization, if that makes sense. So the reason that I wanted to have these gone over was because I wanted to show how to implement them at all, not how to beat a particular implementation speed-wise. Because, again, that wasn't really the goal. In fact, in Handmade Hero right now, we have no bottleneck on something like sine and cosine. So we're not specifically concerned about producing the fastest possible versions. There are cases where you have sine and cosine in your critical path, and you really do care about making sure that they're very fast. That's not really something that we have a problem with on Handmade Hero. So this was more because we just wanted to stop using the C runtime versions, show you how the code actually works, because when there is no magic sine and cosine function, you have to have some way of actually doing it with just adds, subtracts, multiplies, divides, and so on. And so that was all this was for. So we don't really even care. It could be slower than the C version for all we care, and we still wouldn't care. That would be something that we would look at further on down the line if we then determined that some problem with our frame rate was related back to our sine and cosines. Chances are these won't be slower than the C runtime libraries, though, because the C runtime libraries do a lot of that, a lot of extra checking if you ever look into them.
Yeah, I mean, just have a look at this division algorithm again, right? Again, this is slow division. Do not use this in your code. If you use this in your code, you deserve the code you get, all right? I'm just making that clear. But the point here is not that this is fast, because it isn't. The point is to show you the stuff that the C standard library, the sort of stuff it has to do to implement things in a compliant way. This is the industrial strength part here, because industry cares about this. And so that is, that's really the reason why I went through that in not in any detail, but just to show you. And so simply getting rid of that is already a win.
Yeah, and
probably
this happens this is also why we early on in Handmade Hero, much earlier than we would have had to, in terms of getting rid of the C runtime library thing, we replaced square root using the SSE square root. Was specifically, it was not because there's all this much calculation involved in doing the square root, but it's because if you call the C runtime square root, it does a huge amount of preamble work to handle all of these additional cases that have to do with taking square roots of values that we will never take square roots of in Handmade Hero. And so that, is again, one of the big reasons to get rid of the C runtime library, just to get rid of all that cruft. You're already probably starting out ahead, even if you haven't made a particularly well-optimized version. Just not having to deal with all of the sort of IEEE compliance is a huge win in and of itself.
Exactly. And just to rub in this point again, this is not that it's fast. The point of this is that it's branch free, and that's, I think, the basis on which it might be more useful in Handmade Hero. The fact that you can turn this into a four-way sine and cosine might actually be where the real win is. It might not. It might not be the numerical method itself.
Let's see.
Okay.
I think that's it.
Strength. Why am I here? You're here because yes. I don't know why you're here.
Well, to be fair, industrial strength is not really Handmade Hero's thing, right? I mean, industrial strength takes a long time.
This is artisanal. If you want factory produced, you know where to find it.
To be sure, it means the Symbian transistors are not standard compliant. So I don't know. So it depends on. I don't know how well the square root intrinsic is. So eventually, they.
It probably, yeah.
It might just not be C. Like this was the thing that Andrew was talking about a little earlier in the stream, is that there's actually a difference between the C runtime library standard and the IEEE standard. So it's entirely possible to have something like, oh, the Intel square root instruction is compliant with the IEEE standard, but not compliant with the C runtime library standard. Like, that's an actual thing that can happen, right? So I don't know the specifics of that, but, you know, that's just par for the course.
It probably is okay, the square root. That's probably okay. But x87, the old one, actually has a sine implementation.
Yes.
Incidentally. And there's something here in the software development manual that I want to read out to you, because this is very, very important. And that is not it there. I will just find it. And this, if you like, is the reason, is another way of thinking. So there are the instructions there. It's got atan and sine, cosine, and all of that. It's got accuracy. Let me see if I can find this, because there's a wonderful quote in here that I think kind of does this for everyone here. Where are we?
While you're looking for that too, I can add one thing to the question to be sure it means somebody introduced or not sine compliant. Also, the other thing that Andrew mentioned when he was going off one of those functions is also true, which is that just because it takes a lot of instructions to implement something like standards compliance doesn't mean that you can't make circuitry that's very efficient to do so. Like, we may have to do a bunch of bit shifting and fiddling and extraction and all these other nonsenses, and they may be able to make a circuit that's quite efficient that does all those things in a fraction of the time, right? So, you know, don't necessarily take it to mean that something that requires a lot of instructions when there isn't a CPU version of it means that the CPU version will be slow. That's not actually always the case. In fact, it may be unrelated.
Okay. It might be in the optimization reference manual. I might be thinking of a different manual.
I don't think I know the passage you're talking about. I'm interested to see.
Yeah. You know that there are now more pages of documentation for a modern Intel chip than there were transistors in Intel's first CPU.
That's awesome.
Here we go. This is the quote I'm after. This is from the optimization network. Although x87 supports transcendental instructions, software library implementation, that's incorrect grammar, of transcendental function can be faster in many cases. So there you go. That's why we're doing it.
That's nuts. I don't remember that being the case. I wonder if, yeah, well, I suppose it depends if what you were taking. It's because it's yeah. So there you go. There's a little life lesson there. That's pretty great.
Which is that sometimes you can do better in software than you can in hardware.
All right. I think that we will let you get back to your evening, Andrew. I don't think we have any other questions.
It's midday. It is
back to your midday. But thank you so much for taking the time to walk us through that. That was great. And
thank you.
I will go over those routines myself on stream, and we'll work through them again. So that was excellent, and very educational. So thank you so much for taking the time to talk to us.
All right, no, thank you. Glad to help out.
All right, have a good one.
Yeah, okay, thanks, mate.
All right, so that was sort of a brief introduction to numerical approximation sorts of stuff. Again, it's the sort of thing that you can spend a tremendous amount of time doing, and there's people who specialize in this, and it's all they do, is numerical methods for doing things on computers. So, you can take this to the nth degree, and there's people who are probably spending a tremendous amount of time doing nothing other than figuring out how to make, say, for example, the fastest sine and cosine on various chips. Intel, for example, releases libraries of mathematical operations for their SSE chips, where they're trying to work out fast ways to do it, and so on and so forth. And this is basically a whole sort of area in of itself. On Handmade Hero, we're fortunate enough that we don't really have to worry too much about getting the very fastest sine and cosine or anything like that. But like I said, for completeness, I really do think we want to go take a look at it. And that's why I wanted to have somebody who kind of knew how to make one from scratch, show us how to make one from scratch. And that was really good. I think I understand it pretty well now, too. And I was always a little hazy on that sort of stuff because I've never really gone and dug into that sort of thing myself. The only times I've ever used functional approximations, they were pretty straightforward. And I never really tried to do something more complicated like a tan 2 or sine and cosine, which are, more sort of the real sorts of stuff you would be doing for basic math library things. So what we'll probably do is we'll take a look at those again because I'm going to want to kind of go through them line by line myself on the stream, make sure we really do understand them and have internalized them. And then we can go ahead and make SSE versions of them, actually, because there's a little bit of fun in doing that as well. Just figuring out how we're going to implement those in SSE, which is a pretty straight translation. But again, do we want to try and do the quadrant hacking version? Do we want to try and do the lookup table version and, figuring out which one's going on? Maybe we time them, see which one's faster just for fun, anything like that. So we'll be taking a look more at those in the future. But again, thank you very much to Andrew for taking time out of his day to show us how you go about building those things. If you're the kind of person who wants to investigate that path a little bit more, hopefully now you've got some footholds there and you can go. All right, that's it for today. We will be back next week on Handmade Hero when, we will pick back up with our lighting code. And when Andrew's ready with that code, he said he was going to be posting that online as well. And so we'll pick that up and we'll start playing with it with our own version of it at that time. So thanks everyone for joining me, and I will see you next weekend. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.